Hello, everyone. Thank you so much for being here. We're going to start just in 5 minutes, so stay tuned. Don't go anywhere. We're going to come in 5 minutes. Thank you so much. Hello, everyone. Thank you so much for being here. We're going to start just in a minute. Welcome to the afternoon sessions of AI Pulse 2024 here at Master Stage at Station F. My name is Viljana. I'm going to be your MC. I work as a product manager at Scaleway, the organizer of this event. Round of applause. While we have a bit of a time, thank you so much for being here online. Thank you also for joining us. We hope you can see and hear us well. If not, just write us an email. We're going to start with actually one of the best speakers we had last year. As some of you know, actually, AI Pulse 24 is the second edition and not the first one. He was such a great speaker last year that we couldn't resist, and we invited him one more time. Let me present you talking about AI in the fast lane. From autonomous vehicle to ride-hailing and then to racing, from Ampere Computing, Chief Product Officer, exactly, Jeff Wittich. Round of applause for him. This is our first speaker.
All right, thanks everybody. So as was said, I'm going to talk a little bit about AI in the fast lane. And I'll start off a little bit with an intro on what it is that Ampere is doing, what we've been working with Scaleway on over the last couple of years. Ampere, we are building power-efficient processors that are powering the present and the future of the cloud, as well as AI compute. The advantages are that we've built processors that are extraordinarily power efficient. That means that they're also very cost effective. It means that they deliver incredibly high performance at scale. And this applies not just to the more traditional cloud workloads that we've all been working with over the last decade or more, but they also apply to the current generation of workloads, AI inference in particular. So I'll talk a little bit about what Ampere has developed from a technology perspective, how that's being deployed through Scaleway, and what you can expect to take advantage of. But first, maybe I'll just start off with an example of how our processors are being used today. And I think the automotive industry is a great example of that. There's a lot of different pieces of compute within the automotive industry. You have everything from the development of the software and the vehicle platforms to actually powering the vehicles themselves, to monitoring the vehicles and optimizing the experience, and even building services on top of that, say around ride hailing. So this is an area that we've been very active in over the last couple of years. So to start off, the development piece, a lot of the software that's out there in the automotive space has been built on top of the ARM ISA versus the x86 ISA. So that's a great entry point for us. We have ARM-based processors that people can use to natively compile their automotive code, run their CI/CD loops, and we have customers that are doing things like that today. Tier 4, for instance, is using Ampere processors in their CI/CD loop for automotive development. Now we go into the vehicle itself. We've been working with folks like Cruise, which is owned by GM. Cruise needed a high-performance processor that could handle all of that data coming in from the numerous sensors on the vehicle, process that data, and then make decisions real-time during driving. Now, the catch was, it also needed to fit into an extremely small power envelope because all the power is coming from the vehicle's battery, and the thermal conditions are very stringent within the vehicle itself. There's not a lot of room for cooling in the engine. And so Cruise built out an automotive platform that includes our Ampere processors that gives them the performance they need. And frankly, they had no other options in the market. There's no other processor that can deliver this level of performance in the power envelope that Cruise needed. Also, on the vehicle side, Red Bull Racing. This might be my favorite example. Red Bull Racing has been using Ampere processors to do not just their computational fluid dynamics simulations to determine whether they have the optimal design of the car, but they also use it for the pre- and in-race simulations to determine if they have the right strategy. And then lastly, taking it to the services side, we've been working with Uber, and Uber is using Ampere processors to support their ride-hailing service. So you can see here kind of end-to-end, everything from the development to the in-vehicle deployment to the services built on it. All these are high-performance requirements that need power-efficient processors, and Ampere has been providing those to those customers. Now, if we take that a step further with all of the demands of AI, you've heard about it all morning. The compute demands for AI are extraordinary. The use cases continue to grow. These use cases require a lot of compute. And these models that we've been spending the last year or two training, these models will need to run everywhere. As Michael Dell said, we're going to see inference running everywhere, on the device, at the edge, in clouds, on-prem. So we need to be able to deploy solutions efficiently and pervasively, and that means having the right AI compute for the job. And that's what we have been working with Scaleway on. Now, one of the backdrops in Europe as well is that while the power crisis is real everywhere, in Europe it's especially acute. Not only is power expensive, power is also scarce. By some projections, the total power consumption required for data centers in Europe could grow by 3.5 times over the next couple of years. Now, we don't think that that will actually happen thanks to technology developments like efficient processors from Ampere and better cooling and better data center technologies. But that's the problem sitting in front of us right now. Extraordinary increase in demand over the next couple of years. Data centers aren't going to be able to keep up with this. The grid isn't going to be able to keep up with this. And so this is why we've introduced solutions like the COP-ARM instances with Scaleway that involve our extremely efficient 128-core Ampere CPUs, coupled with all of the great services that Scaleway provides. They have incredibly flexible memory configurations, storage configurations, high-speed networking, so everything you need to run all of your key workloads from your traditional web servers and databases, but then also your AI inferencing workloads, running models like Mistral or the Llama 3.1 8B models. So really flexible option for everybody. And there will be a session later today where one of my colleagues, Victor, will be talking about how you can get started and what you need to do to run AI inferencing directly on Ampere CPUs. The quick version, it's super simple. With our software libraries, it makes it seamless to run any of your existing frameworks, call the APIs that you're usually accustomed to using, and get started today. So I thought that I would end with a couple of examples of people running AI inference on Ampere CPUs. Wallaroo is a great example of this. Wallaroo has an end-to-end platform that they've built out to help make enterprises able to easily utilize generative AI. So it's an end-to-end platform aimed at enterprises. And when they started to run on Ampere CPUs versus their traditional hardware choices, they saw a 7x increase in performance as a result. So not only did they save a lot of power and a lot of money, but they also saw huge performance increases because of the unique architecture that Ampere CPUs are able to provide. And they turn that then into applications in computer vision across various verticals like retail, healthcare, and manufacturing. There's a number of other folks that we've been working with as well. Claro has an AI as a service platform that they run on Ampere. Again, they're able to get higher and higher efficiency, and they can make this platform available pervasively, and because it's easy to deploy on efficient CPUs. View.io, View has a platform as well. They have sort of a chatbot-based service that will allow people, say in the medical field, to bring their own data, use that data, easily search through it, and return the results that they need. Also, again, running on Ampere. Tier 4, I mentioned a little bit earlier, they're building an autonomous platform using Ampere CPUs for everything from robo-taxis to autonomous buses for various cities. And then Oshkosh, Pratt Miller, they've been building another autonomous platform utilizing high-performance AI, and they're using this for areas like motorsports, as well as other vehicular deployments. So kind of a wide variety of use cases that cross a number of different verticals. As I said, if you're building AI models today and you need to find an efficient choice to deploy those, Scaleway and using the COP-ARM instances from Ampere is a great option. I thought I'd also talk briefly about what we're doing across the ecosystem, because when we look at the future of AI from a hardware perspective, we envision a world where there are a range of choices. There will be different types of hardware, different flexible configurations of hardware that will be optimal for different use cases, different model sizes, different networks in the future. And so last year, Ampere launched the AI Platform Alliance. The idea was to bring together other hardware innovators and create joint solutions that can be easily deployed by clouds and by enterprises. And the exciting thing about this one is not only has the AI Platform Alliance grown from 12 members to 30 members over the last year, we've expanded it to be more than just AI hardware providers. We've also brought in ISVs building software, and we've brought in SIs, OEMs, ODMs that are pulling together solutions. And if you go and check out platformalliance.ai, there's now a marketplace of solutions that are available that involve multiple technologies from multiple AI Platform Alliance members. So another way to maybe get started on some of your AI deployments or get some ideas about what you can take advantage of. So I encourage everyone to go to Victor's session later today. Go ahead, find out how to get started on Ampere at Scaleway. And I just want to say I'm really excited to be here with Scaleway, and the AI Pulse conference. Really a great shining example of how Europe is innovating in AI. So thank you, and have a great rest of the day.
One more round of applause for our amazing speaker. It's such a great honor to be a partner with such a company. We're going to start in 2 minutes, so please stay tuned. Don't be late. Don't leave this room. Thank you. I have such an amazing team that supports me. Thank you, guys. So, we are starting our next session. Please welcome on this stage, talking about overcoming memory hurdles in AI, performance and choice at scale from AMD, Corporate Vice President of AI Group, Ramine Roane. Please welcome.
Thank you. So, as generative AI increases in complexity, memory starts to become a real bottleneck. Both memory and memory bandwidth are really the bottleneck right now for GenAI inference, and somewhat in training as well. So solving this bottleneck is really key to enabling the next wave of AI innovation. And in this talk, I'm going to talk to you about how we go about solving this bottleneck at AMD. So first, do you remember this? This is what happened during the COVID crisis, where there was a misalignment between supply and needs. A lot of people did a lot of panic buying, and then there was a supply shortage, prices went up, and people ended up stuck with a lot of goods that they didn't really need. But then a couple years later, ChatGPT got released, and there was a lot of excitement, and something similar happened with GPUs, where a lot of companies started to buy GPUs, CSPs bought an awful lot of GPUs, and even VCs bought GPU compute time for the startups that they had invested in. And that also turned into a misalignment of supply and needs. And then there was a huge supply shortage that followed as well. But to be honest, that was also caused by the fact that at the time, 2 years ago, there really was only one choice for data center GPU for AI. AMD had data center GPUs, but it was for high-performance computing. So it was more focused on a lot of 64-bit compute rather than 16 or 8 or 4-bit compute. But then, starting in January this year, we came up with a competitive product that has the same compute power as the H100, but has almost 2.5 times more HBM memory and 1.6 times the bandwidth. And again, I'm talking about memory and bandwidth because those are the bottleneck for the generation phase of a LLM. Typically, the prompt phase is compute bound, and the generation phase is memory bandwidth bound. But the LLM also needs to fit into the memory. So the weights need to be able to fit into the HBM in order to just run. So memory capacity is also really key. And again, you can see there is a ratio of 2.4x in terms of memory here. So earlier this year, by the way, Satya Nadella from Microsoft announced at Microsoft Build that they're now inferring ChatGPT also on the MI300X, and that gives them the best price performance. So that's a super big model, but I'm going to give examples of smaller large models that can show literally a 2x TCO advantage. Basically, 1 GPU versus 2 GPU, or 1 server with 8 GPUs versus 2 servers with 8 GPUs. For example, if you take the Llama 70B, so that's 70 billion parameters, assuming you're using FP16, that's 140 gigabytes of memory just to fit the model in the GPU. So H100 has 80 gig, so 140 won't fit. So you need 2 H100s to just infer Llama 70B. Whereas the MI300X has 192 gigabytes, so more than 2 H100s. So it fits in 1 GPU. So it's same GPU, same power in terms of watt, same compute power, just 2.5 times more memory. And if you look at the smaller Mistral, the bigger Mistral, same story, right? The smaller Mistral is 1 GPU versus 2. The bigger Mistral, it's 2 instead of 4. And then a Llama 405B would fit in an entire AMD server, 8 GPUs, whereas you need 2 of them on the other side. So for basically medium, large, and very large model, you get a huge TCO advantage. And OK, so that's great, but how about the roadmap? Well, we also happen to have a TikTok roadmap every year. And we continue to have a memory advantage along the way. So the question is, how do we do that? I mean, NVIDIA is today the biggest company in market cap. How is it that we can do 2.5 times or twice the memory? And the secret really is advanced 3D integration in package. And that's a technology we developed for EPYC, our server CPU, pretty much 10 years ago. That started with chipletization of the CPUs. And then we added a 3D component in the CPU. It was a cache, a massive L3 cache that was sitting on top. And for GPUs, we took the same approach. And we basically, on the bottom there, in the orange, we put the whole cache memory hierarchy and the IOs. And on top, we put just the GPU dice, nothing else but the GPU dice. And they talk to the IOs and the memory hierarchy vertically, surface to surface. And that 3D integration gives more room in the package to put more HBM. That's how we do it. And that's a technology that right now only AMD has and has had for several years now. Even our previous GPU, that was the HPC GPU, the MI250X, was using this kind of architecture. So it was chipletized and it was silicon on silicon. And that GPU, the older MI250X, as of today, is still in the #1 supercomputer in the world, #1 on the top 500 list. It's a 1 exaflop of FP64 GPU. So that's how we do it, but great. Hardware technology, fantastic. We've seen that before, but we all know that software is the bottleneck, right? So how about the CUDA mode? Well, we found out there is no CUDA mode when you're doing a GPU, because having a GPU, it's basically CUDA compatible. So if there is a mode, it's got to be a library mode, like all the libraries that have been developed to accelerate linear algebra. Well, there is no mode, because every time you do a new generation of GPU, the memory hierarchy changes, and you have to rewrite all of your libraries from scratch, because those libraries are all about memory tiling and so on. You need to rewrite everything from scratch, so there is no mode. We are at the same level playing field every time we do a new GPU. And on top of that, we work with the ecosystem, the open source ecosystem, to make sure that the softwares out there are hardware agnostic. So we work with Hugging Face that does continuous integration and development on our GPUs. Same for the PyTorch Foundation. Same for JAX. And more importantly, OpenAI has a compiler they call Triton. That's the OpenAI Triton logo over there, which is a hardware agnostic, a GPU agnostic programming language where you can build a transformer and write optimized kernel at the higher level than CUDA, and it targets all the GPUs. So that's completely vendor agnostic. So it enables you to basically not be vendor locked. And that's really to conclude. I wanted to say that choice basically removes all the risks that are associated to being vendor locked, whether it's supply shortage or a problem they may encounter one day with manufacturing, or even just having the best TCO for your specific use case. For one use case, this may be the best solution. For the other one may be the best solution. But in order to be able to have a choice, you also have to adopt vendor-agnostic solutions, open source solutions, like Hugging Face models or VLLM for LLM inference runtime, for example, or PyTorch, and so on. And that would basically enable you to break free from being vendor-locked and go to a more open solution that supports everyone. And you heard this morning that Scaleway announced availability for the MI300X. So if you want to try for free for a few days to see what you can do with 2.5 times more memory, you can just go to the Scaleway website. I believe there is a link there to go to the GPU instances. So it's Scaleway, I think AI, and then GPU instances, and then you fill up a form to get into a waiting list for evaluation of the MI300X, and they will provide you a few days free, and you get the support that you need as well. Okay, thank you very much.
Ramine, thank you so much. It was absolutely great. Now I know that I'm going to use a TikTok roadmap, I think you said, for my devs. We're going to see each other at 14:35. So you have a bit of a time. Take pause and come back to us. See you around. We're going to talk about AI sustainability. So, how are we feeling? We're going to talk about AI sustainability. And we're going to have amazing 4 speakers. It's actually going to be a panel, so be prepared for the hot discussion. And I will present you shortly our 4 amazing speakers. So it's going to be Gael Varoquaux, Samuel Rincé, Stéphan Llama et Daphné Leprince-Ringuet. Voilà.
Hi, everyone. Welcome. My name is Daphné. I'm a French tech reporter for Sifted. Sifted is a European online media publication that covers European startups. We're here today to discuss, as you just heard, sustainability and AI. It's a side effect of AI that is increasingly known and talked about, I would argue. I think today has proven that as well. I would also argue that it does tend to be kind of comfortably brushed under the carpet as well by some players as a second thought and a kind of annoying side effect of AI. So it does feel like there is more talk about it, and that there has been in the last year and a half. There are reports coming out fairly frequently about the impact of AI on our planet. There's just as an example, I think I saw yesterday, there was a report from ADEME, the French agency dedicated to the ecological transition, that mentioned the environmental footprint of data centers and mentioned AI as part of this growing footprint. So, there's more and more out there about it. So it can feel slightly paradoxical that we've got more awareness of it, but at the meantime, we've got more and more investment into AI. All it takes is a quick look at the data around VC funding for AI companies to see that AI is everywhere and all at once at the moment. And I'm not sure that all of these companies kind of mention the environmental footprint of their technology as part of their pitch deck necessarily when they're raising VC money. So what is really done today to enable greener AI? Is that enough to face the scale of the problem? What more can be done? And if it's a problem today, what will it be like tomorrow when AI becomes even more of a commodity around the world? Those are all questions we'll be discussing today. And to discuss them, I'm joined by our fantastic panel. We've got Gael, who's the research director at INRIA, the French Computer Science National Research Center. Gael focuses on the application of AI tools to health and public health, particularly. He's also the co-founder of Probable, which is a newly launched part public, part private startup that aims to build and share open source tools for AI. We've got Samuel as well here, who is the co-founder of GenAI Impact. This is a non-profit organization that is dedicated to understanding and mitigating the environmental footprint of generative AI. And we have Stéphan and Eloïse here next to me, who wears many different hats, as we discussed before, but they're all linked to your main focus on machine learning. Stéphan Eloïse is an assistant professor at CNAM and at Sciences Po Paris, and also an independent board member of Probable. So we've got two representatives of Probable here today. To kickstart our chat, I wanted to go back to about a year ago. I think it was about a year ago. I was talking to an AI founder, and I was questioning him about the environmental footprint of the model they were developing. This founder will remain anonymous. When I asked him about how much he was thinking about it, he kind of said, I'm focusing on developing the technology now, and I'll focus on the environmental footprint later when the model is developed. Would you say that this is reflective of how founders and businesses in general, organizations in general, really are thinking about AI and the environmental footprint of AI today? Would you say things have changed in the last year? What's the kind of state of play here? How much is this on people's minds?
Maybe I can answer a bit on that. I think it's true not only for AI, but IT in general, like the awareness around green IT and the environmental impact of IT. But to talk about specifically AI, I think there's one actor that I didn't expect it from them, but it's good to see that. It's Meta. They are making their models open, like you can download Llama and so on. But they also release basic calculation of the environmental footprint for training each models. And this is something to I think, encourage for other providers. Can talk about OpenAI, Google, and others. Try to disclose this type of numbers. And one thing we can notice looking at Llama models is that the training, the footprint for training is increasing each year on year. I think for the first models, Llama models was about 70 billion parameters. Llama 1 and 2 was around 200 and 300 tons of CO2 equivalent. That's about 100 flights between Paris and New York. And the new model, Llama 3, 70 billion parameters again, it's around 2,000. So it really increases. Here it's almost a 10x in 1 year. So that's definitely something to look at in terms of training. And I'm sure we'll talk about inference as well after.
Yeah, I'm glad you brought up the Meta example and the fact that it's the only company I can think of that releases these kind of data. I'm sure there are others, but how mature would you say the sector is today in terms of this transparency? And I guess I'm not only asking about whether there is enough transparency, but is there enough in terms of tools, in terms of standards, in terms of methodology? Where are we at with that in terms of enabling companies to be transparent with their environmental footprint?
I think, well, talking about impact is definitely a huge systemic issue. And not only if we take AI, but as you nicely put in your introduction, I mean, AI is pretty much everywhere. So in terms of market, trying to understand how do we evaluate the impact of the market and the carbon footprint of AI in general. And for me, the question of transparency is also a question of like agreeing on the terms of the debate, and what do we call impact? What like where do the numbers come from? So it's not only like a transparency of just the corporate world and like the organization sharing what they're actually emitting in terms of carbon footprint, but also a transparency on like how do we agree and engage on the conversation about AI carbon footprint. So my take would be, definitely this is a global issue, but maybe we can discuss that a little bit later. It is definitely a global issue on which it's difficult. So any commitment and any intent to actually bring some novelty in the debate so far, and as of today, I think is very much welcome, because in my opinion, AI as a market, I said again, is pretty much late compared to other sectors of activity.
Well, yeah, maybe on this topic, so on the topic of transparency, I have witnessed a battle of narrative between people. For instance, let us quote Sasha Luciani, who's one of the very strong person on this, coming up with different numbers than some big actors, and literally having debates on social media where some big person in the big actors questions the numbers that Sasha comes with. And so here, there's no way out of this, because the actor has a better way of assessing the impact. So the only way forward is that the general public and the general narration demands this assessment, because if it's done on a voluntary basis, then there is really no control.
No one said the greenwashing word, but I'd imagine there's also
not yet
a bit of a risk around that. Great, thanks. So we've talked about how to measure the impact of AI models, which is obviously a huge part of solving this equation. But obviously, if we take a step back, it starts with reducing the consumption in the first place, which is something that came up a lot in our prep talk. Gael, actually, during our prep talk, you used a really nice metaphor that involved SUVs, bicycles, and bakeries. Would you like to tell us a bit more about that and what you meant by it?
Well, it's not only a technical problem. Most of us are from a technical background, so we think of things with a technical term, but it's a behavioral problem. It's how people use tools. This is what creates impact in two ways. First, because when you use a tool, you consume. But second, you also shape the market, right? It's the customer who shapes the market. So back to SUVs and bicycles. I live in France. There are bakeries everywhere. And I keep seeing people parking their huge SUVs in front of the bakery. And I just don't understand. Is this bakery really good, and do they have to travel really far? And, a lot of us are innovators, and one metaphor I would like to have, and once again, maybe it's going to speak more to the French people, but let's go back in time. Let's think, about their great inventions. Are we going to invent the Concorde? So the Concorde was a plane that was going very, very very fast from Paris to New York, or are we going to invent the TGV, the fast plane? Those are both technical inventions. They shape the world in terms of sustainability in a different way.
So, which bakeries deserve an SUV? I like to come out with a metaphor now. If we're saying that's not all, basically what you're saying is not all use cases require huge models that consume a lot of the world's resources. Is it too soon to have kind of this use case deserves the LLM, this use case doesn't? And if so, what does this kind of chart look like today?
I'm not going to tell people how they work in their own business. I'm not an expert. All I can say is that when I work on a vertical I understand, for instance, health, I evaluate things on a case-by-case basis. And the really important thing here is to evaluate, not to evaluate a benchmark performance. Health is a good example. I could be evaluating a diagnostic benchmark performance. That's not what really matters. What really matters is public health, is how healthy is going to be the person 10 years down the line. And, some diagnostics are more important than others, and trying to, maximize diagnostic on every single information is not going to work. And we're talking a lot about ecological sustainability, but this also gets in the way of economical sustainability.
And maybe I can add a bit more on that. If you're today an organization and you think about integrating AI, or you already done that, I advise you to look at what the AFNOR did with the Ecolab and some actors and experts in terms of AI and environmental impact. They published the AFNOR spec Frugal AI, and basically they talk about frugality instead of efficiency. Basically, efficiency usually don't reduce the environmental impact. Like, efficiency will reduce the energy consumption for one request, for instance, for an LLM. It will reduce the cost as well. But like we see every time that the usage, the global usage increases. So in the end, the impact is not reduced. It just grows bigger and faster than before. And frugality is about like doing efficiency, but before implementing and doing efficiency, think about the usage. Like, do you really need AI to solve your issue? Do you need generative AI, or can use traditional AI models? And then you can think in a framework where you operate your AI models within the planetary boundaries, making sure that you can measure, estimate the environmental footprint of your service using AI, and make sure to reduce it and cap it to avoid like rebound effects, things like that.
Yeah, something I'd like to add is, like when we talk about the footprint and the sustainability, I think it's also important to take into account the whole value chain of data. Because, like we're talking about AI, but basically we're talking about, data economy. And I think that, and I totally agree with Samuel, difference and distinction between efficiency and frugality. However, I would say, if you want to change, again, like business practices and the industry practices, you need to speak also their language, and like look at how, like I think it's Sacha Lucioni actually who showed that basically she estimated that for ChatGPT to come out, it cost, like the compute power cost was about $700,000 per day. So, like imagine that you have to fund that, and you have to make it accessible, and you have to scale it. So it's just, not only a matter of like sustainability regarding just the carbon footprint. It's also like a whole, like design of how do you look at what kind of, use case, what kind of tool you're bringing to respond to the use case. How do you frame the use case? How do you, distribute the compute power? How do you build the data pipeline? And how do you make this both efficient but also sustainable?
Would you say that this thought process is well understood today in the sector? Is that something that people receive well and are like keen to do?
I think people don't have the right mindset. For instance, I worry much less about the training of a large language model. It's very impressive, in terms of power consumption, in terms of money involved. It's very impressive. But should we be successful? Should these things be massively used, then their inference cost, whether it's in terms of dollars or in terms of carbon footprint, is going to be what drives down everything. And there are real questions here. So I think the real question, and you mentioned rebound effects, and I just want to unpack this just so that everybody thinks about the problem. The problem is that we are, by the way, going to do efficiency improvements. We are doing efficiency improvements on these things all the time, but their usage increases faster than the efficiency improvements. And should we be successful, this ideally, everybody in the world uses the best technology to solve the best problem. And so for this, it needs to be appropriate.
I want to add something. I think it's important, and like I totally agree with Gael. It's very important to educate not only like a small portion of like that global value chain, as I said. So like train developers and engineers to be sort of like there's a greenwashing about like being green by design, but however also to be aware that it's a collective sustainability that we have to build. So if I'm a VC and I'm like investing in a company whose compute power is absolutely not controlled, and I, like, how do we sustain that? And if I am a developer, I mean, it's pretty much common sense question. But again, there's no common language and common reference or KPIs to lay on so far. So I think that's one of the major issues that we need to tackle collectively also, is like to build that sort of like global KPI agreement from the AI sector.
Yeah, I completely agree. Like, what type of KPI and measure you can do, it's really important. And I talked about Meta just before, and I mentioned that the computation for the carbon footprint was very simple. It's very like number of GPU I have, the power consumption, the time I use them. I have the energy, and I convert that into carbon emissions. In reality, and Sasha Lucioni talked about it in a paper, when you train a model, you can do this basic naive estimation, but in this paper, they did a more broader approach, and they compared the two. And between the naive approach and the more accurate approach, it's ×5. So you multiply the numbers of Meta probably by 5 just to get a more realistic number that still lacks information in it.
If I can beat a dead horse, because this has been mentioned many times, yes, it's a question of the discussion. We're thinking, how do we get solutions? But we're going to get solution if the discussion is anchored on these problems. So it's back to those numbers, because many people think about problems, and if many people think about these problems, we're more likely to get a solution.
I wanted to talk a bit more about whose role it is to change this outside of, obviously, of the builders, of the developers, of the businesses. I'm thinking of the funding ecosystem that's enabling these companies to not necessarily build the right tool for the right use case. Is there something to say there as well? You mentioned that VCs and kind of VC money as well. Is there something here as well that we need to look into?
Yes, it's something we definitely need to look into. Honestly, I don't have in mind any like venture capital, and I think it's there's a space to be actually developed for and to be occupied for a VC in terms of like claiming that they are sustaining AI that is actually sustainable. I think everybody is trying to figure out how to collect that data also, and how to actually understand what's the real emission. How do we make net zero? I mean, it's hopefully one day net zero emission. How do we, I think that the reality is that the ecosystem is moving too fast. So, and there's a lot of X washing, either any kind of topic is kind of like, very hard to rely on. I think it's also, so as a scientist and as a researcher, I think it's also something that we need to figure out from our chair, how do we, and also for Gael, how do we maintain sustainable condition for research, so that we can actually audit, we can actually build that consensus on what is sustainability around AI.
Any thoughts to add?
And I think one great way to do that is to push for open source AI. Of course, because you share the training impact, so we can gain a bit of that. But also open source tools to make model more efficient, for instance. And also finally, and it's part of the work I do at GenAI Impact. It's support open source methodologies and tools. We're building Ecologit, which is an open source Python libraries to estimate the environmental impact of each inference you do to OpenAI, Mistral, any provider. We have many. There are also other tools like Code Carbon, where it can help measure the energy consumption and carbon emissions when you run AI workloads, like on your laptop or on your server. Or, and one last, Green Algorithm, which is a tool that enables like planning and scoping AI workloads and get an estimation before running the workload of energy footprint and carbon footprint.
So yeah, the first step really you'd say is to kind of fill that information gap thanks to tools and standards that are applied to everyone. So we talked about the founders, the developers, the funders. I wanted to talk as well about the role of governance. This is something that you've worked a lot on, Stéphan, of course. To what extent would you say governments have understood and taken on this challenge when it comes to understanding and mitigating the environmental footprint of AI?
So I'm going to be quite honest. Again, it's still an education topic here. Like when it comes to, I think the over-focus on GenAI over the last couple of months and years have sort of blurred the conversation around governance and carbon emissions around technology in general. I think this is a new topic, as I said earlier in the panel, but also, it's been completely overshadowed by the GenAI bubble or explosion. And I think, for governance, I mean, there are already some, attempt and very vocal, I would say, in Europe more specifically when you look at the AI Act. But maybe Gael, you want to say a word about it after? No. So there are some attempts to regulate or to have at least look at that. I think the first step for regulation, as we said earlier, is transparency and like capability and auditability of systems. The second thing is also education when it comes to understanding the value chain, because everybody, when we speak of GenAI, everybody thinks of like fine-tuning, but there are other techniques such as like RAG or open model of experts, sort of a approach to both efficiency but also carbon reduction. Yes, sorry. So definitely, understanding that we will work by working on transparency, we will bring better regulation and also more adapted to also the business world's needs. Like when it comes to sustainability, will be a major improvement.
If I may, maybe on the topic of governance and possibly regulation, and also which actors are important. Regulation and governments are results, not only, but partly of the public discourse. And I mean, we've seen this yesterday morning. I'm sorry to bring this up. So an actor that's really important is all the actors of the information sphere. So first of all, thanks to the organizer for putting us on stage to discuss this. The discussion shapes the actions of individuals and of governance.
You mentioned the EU AI Act. I know, Gael, you didn't want to say more about it, but it would be interesting to, because it's, I guess, one of the only texts out there in terms of governance that's governing the environmental impact of AI. Feel free to correct me if I'm wrong. Where does it leave us, the EU AI Act, today? Does it show that governments have understood this issue, or would you say it's falling short of expectations?
I wouldn't say it's perfect. Like if you read the AI Act and the part that talks about sustainability, it's really 2-3 bullet points. So it's very light. It concerns specific models, so called general purpose models. So either it's a very big one, a big model, or it touches a specific use case that is very sensitive. So if you fall into that category, in one of each category, you have to report or estimate training impacts and energy. It doesn't talk directly of inference, so here we're missing one part, and I mentioned at the beginning, like last year with Data for Good, we wrote a white paper called, it's in French, so Les Grands Défis de l'IA Générative, and we made an estimation to compare training impacts of GPT-3 with inference for 1 month in January 2023, so it's a pretty old number. Training was about 500 tons of CO2 equivalent. And we did a calculation with the scale of ChatGPT at this time, January 2023. And we arrived at 10,000 tons of CO2 equivalent. So it's times 18 almost, or 20, the impact on the same period of time. Like training GPT-3 is around like 2 or 1 month, 2 weeks or 1 month. And using ChatGPT at the scale of ChatGPT was about like 10,000.
Yeah. I don't know if you wanted to add something on the EU AI Act particularly. No.
No.
Sorry. I saw you. Okay. I guess my last question would be, whether you're thinking in terms of the future of governance or the future of just where society is going and how much as a developer or as a founder you're going to have to be thinking about these issues, what would you recommend in very practical terms that founders who are working on these models implement today?
As technology providers, we can't solve all the problems, but we do shape the landscape. And so what I usually say is choose what you enable, choose what you facilitate. So think, you're creating technology in all kind of different ways. Think which actor you're going to enable and what you're going to make it easier for them to do. And that's, that goes along the whole chain of construction, from the details of your AI or machine learning algorithm that you use, its sample efficiency, its cost, to the UX, to your documentation, to everything.
We probably have time for 1 sentence each.
Well, I would say use, contribute, and fund open source ecosystem.
I'm going to be practical. I would say let's work on how do we shape and design the use cases for AI, and keep all that conversation, all the topics in mind, and especially how do we make it frugal but also efficient, right from thinking about the use case, what is the need really, and how do we make something sustainable around that, answering that need.
By design, then. Thanks so much to the three of you for this really interesting panel. Please join me in a round of applause for our phenomenal panelists.
Thank you.
And one more time, because it was an amazing panel. Thank you so much, everybody. That was perfect. We're going to see each other in 10 minutes. Stay tuned. We're actually going to have the company here on the stage that calls Meta. See you around. So take your seats. I see people coming. It's okay. We have a few seconds. So we're going to talk about AI at Meta, Llama and open research at scale. And so we are lucky to have actually one and only product lead generative AI research from Meta, Keller. Please welcome him. Whoop.
Thank you. Thanks, everyone. So my name is Keller. I'm a product manager at Meta. I've been at Meta for 5 years, and I'm currently based in Paris, but I started off working on a product you might have heard about called PyTorch. And PyTorch is a leading product we use for developing AI that's open source that I hope you've all tried if you build AI. I'm a big fan. So my colleague Nela can't make it today, so she's sorry, but I'll cover the whole research. So, all right. So AI, it's everywhere right now. We see it in products we deploy at Meta. We see it for large language models. You might have tried ChatGPT. You might have tried Llama. Everybody's using it. I know, like, as a product manager, I write documents all day, so it's definitely a power tool for me. Text-to-image generations. I don't know if you've tried to make birthday cards last minute, because you might have forgotten someone's birthday. And also creation tool in general. So we're seeing it everywhere today, but how has it come here? You know, how do we build this AI, and why is it going so fast right now? So we'll talk a little bit about how AI has evolved, especially at Meta in our research. And so we started with AI initially being mainly focused on recommender systems. So that's the thing that you have, like, on Google, for example, when you type a search and you want to figure out, what's the best, most link that people should click on, or that they'll be relevant for them. What's the best ad to show a user? What's the next message to put in your feed? And so these were the focus for a long time of research, and where, like, a lot of companies derive value from. But AI has evolved, and AI more and more can understand now things, understand text, understand images. And so we're slowly going from now a stage where we have a good understanding of things, where AI can kind of make sense of objects, of text, to an AI that's going to start being able to think, where we're going to add reason, where AI is going to be able to do plans. So how is that going to happen? I'll try to distill a little bit how we're thinking about it at Meta and how we're hoping to get to AGI down the road. So we've been an industry leader in AI research. In Paris, we had our first big lab outside the United States that got started. And that's over 10 years ago. And with that, we've contributed to the AI ecosystem, where a lot of our alumni even have gone and started other companies that have done great here. But for us, AI has started. I want to show you this example where, like, in 2012, we were working on image understanding. And the work that's been done until 2019, and there's even more that's coming. But in 2012, we would be able to give an image and show and ask, what's in that image? And we'd be able to identify that there's a bus, there's a clock in it. That goes on to being able, later on in 2015, to identify where those buses are, where the clock is, and put a box around it. 2017, we can, more than a box, be able to identify each of the pixels that represent the bus. To then, in 2019, detail everything from the background to the foreground and classify these objects. So it's going really fast. And similarly for videos, now we add more and more details. And so that helps down the road for some of the examples that we've showcased earlier around creativity, to be able to work on images with text and be able to extract information from them. And models are getting larger and larger. All right, so where are these things deployed? I'm talking a little bit about images because I have a long section on, like, LLMs at the end, so I'm trying to showcase a little bit of the various elements we're working on. But that means that today on Instagram, you're able to edit images, find the dog, move it into a different picture, change the background entirely. And this is something that would have taken, like, a professional editor hours to do before, that can be done by anyone today on their phone. It also has like social impact, where we're able to leverage it for medicine, for the environment, and I'll list at the end a little bit of some of the projects that Meta has helped with. All right. So in 2024, FAIR, our research lab, has come up with a lot of different papers. One of them, I'm going to call it a couple that I think are worth it. VJEPA and Code Llama. VJEPA is, if you haven't looked at it, is one of our efforts that's looking at beyond autoregressive LLMs and trying to understand where we can improve models at scale for reasoning. And so looking at logic, looking at world understanding. And so this is an attempt at doing this. Code Llama is built on top of Llama for coding. And so every quarter we release papers. We have very much of an open research approach that I'll discuss. So talking about beyond LLMs, beyond autoregressive LLMs, how do we get to AGI? So I'm just showing this one slide. There's much more on our blog. But at the end, we have this approach that goes beyond the LLM, that takes into account, I think one of the key terms here is the world model with memory and all orchestrated around it, so that by the time the model has perception and understand like a given situation or environment, it can take an action and understand the consequences of that action in that environment, how it's going to change it. So finally, the innovation we work on at Meta is not just the code, it's not just the model. We're also developing our own silicon. And the reason for it is there's been a trend today, for example, around transformers. And so they're being used in many, many areas. And so we want to be able to deploy these models at scale. And to do that, we need more efficient ways to inference on them. So the open approach. It's been like one of our key tenets at Meta. We strongly believe in open research and in open source. These are different terms. The open research term shows that any of the research we do, we publish it. And so we give it access to the world so that others can replicate it and use it. And so we've got many different projects that came out, like Excel Formers, PyTorch, which I've worked on personally, that have allowed the community to grow and to build on top of each other. So that helps accelerate innovation for all. So it helps developers because it gives them a set of tools readily accessible that are usually deployed in all the major service providers. It helps Meta also. I mean, we're not just altruistic on this one. It really does help us because it does a few things. One, it helps like direct the research in a direction we care about. It also helps when we're hiring somebody, if they're using the tools we're using, to onboard them much quicker. It helps because at the end, the vendors that build, let's say NVIDIA that builds chips, will leverage our stack, which is going to make it more efficient. So it helps us. And finally, it helps the world because at the end, it accelerates this innovation for all. So this wouldn't be able to be done without all the partners that we've built over time. So there's a few names here. You recognize Hugging Face, that's also based in Paris and where you should all get your models from. All right. So Llama. So I've worked on Llama 3. I started working on Llama for the launch of Llama 3. I led the pre-training stage, helped the planning for post-training. And so here, I'm here to talk to you a little bit about like what Llama 3.2 in particular does and how to leverage it. So Llama started in Paris. Llama 1, Llama 2 were mostly built here in Paris by the teams at FAIR. And it's taken off. So now we've got teams working on Llama around the world, in the United States, and here still. We launched Llama 1 and then Llama 2 shortly after that, and followed by Code Llama. Llama 3 is the big launch we had this year, and even with Llama 3 alone, we already had a Llama 3.1 and 3.2 release. The 3.2 release started taking Llama beyond the text and into the world of multimodality and understanding of images. So we've got over 400 million downloads. I mean, when I think about it, the number really surprised me because our target users are researchers and developers. I don't think there are 400 million researchers in AI out there, but that's that's how many downloads we got. People wanted to try it. They tried different versions of it, and allow them to iterate fast. So yes, so one of the things also with Llama is a lot of people that ask me, like, where should I start if I want to try to play with an LLM? So if you're not like a researcher, I said, look at any of the APIs out there. They're going to be the fastest way for you to build a proof of concept, to test out your ideas, see if there's a product market fit for your tool. But at the end, if you want to scale, at a given like model quality like mark here, like the 2 dotted lines you can see are at, we're comparing an MMLU. Models are like around 42 or above from MMLU, and the ones that are over 86. So that's just one benchmark. So you can recreate a similar graph for a lot of the other benchmarks. What we see is that over time, Llama now has become the cheapest model to deploy at an even at the same quality. So when you're thinking of scale or deploying a model for your enterprise, that's the best solution. So let's talk a little bit about the different models, because Llama is the brand. It's the one model that we have, but it's not just that. Llama is a large model, the frontier model, that's 405 billion parameters, but that's not the one that's used most of the time. The ones used most of the time are smaller models. There's 70 billion parameter models, 8 billion parameter models, and they're also the multimodal versions. In addition to that, we don't just launch Llama, because one of the things compared to other vendors that have like API access mainly to their models, we open source it. So we want to make sure that people that leverage the model in open source are able to also use it in a safe manner. And so we propose also a set of safeguards, and we educate how to do that. So I'll dive a little bit into how to launch these models safely that you're getting from open source. So one of the themes for this conference, if you've noticed, has been like AI on the edge. Like, I think, was it Michael Dell that was saying something of bring the AI to the data, not the data to the AI. So that's really important. Like, more and more we're seeing that depending on the application that you have, you want to be able to deploy small models on the edge. And so we have Llama lightweight models at 1B and 3 billion parameters, as well as the safeguard that comes with it. And you'll see that every model that we have has the matching safeguard. So same example with the vision model. I'm not going to dwell on this one. All right. This slide and the next, I'm not going to dwell on it neither. It's just to show that our models are leading edge. Whatever size you're looking at, they're going to be either state-of-the-art on some dimensions or at least close to it. Now, when it comes to choosing a model for deployment, one thing to keep in mind is not all the benchmarks are going to matter to you. So figure out which benchmark matters to your company, to what you're trying to do, and also figure out, can you make this benchmark better? Can you improve it? And with open source models, we're able to take it, add fine-tuning on top of it to improve on specific areas that you're willing to improve. Okay. So the Llama stack. The Llama stack is our solution to help developers more readily deploy models. And that's taking into account that we're putting out updates quite regularly. And so there's always a friction in adopting a new model when there's an update. So how do we do that? Llama Stack is here to create a layer that's going to be consistent for developers, whatever the model version or how you want to deploy it. So if you want to deploy your own model, or if you want to use an API that's provided by one of our partners, you can still have the Llama Stack that will look exactly the same to you in terms of what you need to call to run the model or how you want to fine-tune it. So it's got 2 different main categories. The first one is the Agentic System API. The Agentic System API is really everything that goes around like launching and inferencing the model. Like, can you connect it to a memory? Can you connect it to specific tools? How do you want to manage your prompt or your system prompt or pre-prompting for some of the users? The model toolchain API is here around figuring out, like, how do you do inferencing? Like, can you fine-tune your model? Like, how do you do that in a way that's consistent? What's your data pipeline, and how do you tie it to your model and your workflow? So at the end, it helps both the developers and the providers. It helps the developers to make it easier and faster and consistent for them to use. It also like applies some of the best practices that we have and we've developed, and the same we use internally at Meta. For the providers, for them, it helps us focus on what matters, which isn't around like the integration piece, but around differentiating what's behind on their stack, the hardware they have, the distribution, and the pieces they're really good at. So this is a shameless plug for Executorch. If you haven't heard it, tried it. This was my pet project for the longest time at PyTorch. It's the runtime that you use to deploy AI on device. That's what we use on our AR glasses. That's what we use on our mobile deployments. That's what's used also in partnerships with several other companies that we have. And so it's got some Llama-specific launches. That's what we use in the Llama stack. And it's got very little overhead. So highly recommend trying it out if you want to launch Llama on your phone. And TorchTune also is, with PyTorch, the partnership that we have here, the way to tune your model seamlessly by staying in the PyTorch stack. So I know for a lot of developers, it used to be tricky because you had to go from the moment you did the research and the development of a model on PyTorch, let's say, and then the deployment where you had to figure out what was unique and specific about the hardware you were deploying to. Did you have to use, CUDA? Was there an abstraction? Did you have to convert to a TensorFlow model maybe to deploy it on certain types of hardware? And so PyTorch is helping you stay there, but also stay there enough for the fine-tuning process. So I'll give you a minute if you want to scan the QR code and learn more about Llama Stack. But this goes through pretty much like how to launch it and how to set up your system at scale with Llama. So trust and safety tools. Our process for development takes into account safety, like from the very beginning, in terms of what types of data we ingest, through benchmarks in the middle to see how our model is behaving, all the way to the end of deployment time. And it's a cycle where we keep learning from it. The one difference, I think, as I was mentioning, is because we give these models in open source, we have to think about not just like inference time mitigations to the problems that we have, but we have to also think about what tools can we give people so that these deployments can be safe. And so I won't list all of them here, but I do want to call out that safety happens both at like the input time and also at the output time to check what's happening. So for the input, you want to check things like, is there a type of prompt injection that's being done? Or is the input in line with the types of questions you want to allow the model to respond to? And same on the output to try to figure out, to make sure that the content is safe for integrity or for safety purposes. So building AI responsibly is what we've been doing since the beginning. We have system cards. We have model cards for all our models. We also have work with the AI Alliance, which is a group of companies that tries to set standards around how we approach safety, and also through open source, because we believe strongly that when things are in open source, others can look at it, can critique it, and can tell us like how to make it better and safer. So again, if you want a guide on how to deploy your AI safely, please scan this QR code. So what's next, the future? What can I tell you? So there's more than Llama 3. There's Llama 3.x, like we're at 3.2 right now. But for the next generation of Llama, we'll have longer context. Well, that's one of the things we need to work on, and we know it. We've heard it from the community, and we're going to increase our context length. We're going to also add more modalities, both at the understanding phase, around like what can our models understand from the perspective of images, videos, can they make sense and reason around them, to what they can generate, also whether it's like speech or images or videos. And finally, we're looking at more integrations. So today, Llama 3.2 is deployed on all our surfaces at Meta. We are deploying it on Messenger, Instagram, Facebook. Not in Europe yet. No, watch out. Might come, might not. We'll see. But if you travel, you can try it out, and also you can see some of the examples online that have been done. And you can replicate a lot of it with Llama already yourself. So It's also used beyond our family of apps, like in advertising, where we're starting to include it into our advertising stack so that people can, small, medium businesses, for example, can start campaigns like at scale with things they wouldn't have been able to do without these tools. And also on all of our devices. So I do not have Orion glasses. I've been asked to try out today, sorry. But they're great. And we do look more and more at different surfaces where this AI can be deployed. Because LLMs, at the end, like, while they do a lot of things, one thing I think they're going to be really good at is to improve UI, improve the user interaction and experience. They can help better communicate with the machine back and forth in different types of modalities. And with glasses in particular, we do believe it's one of the key devices in which they're going to be deployed because they have your context. They see what you see, they hear what you hear, and you're able to, through multimodal models, engage with them and ask them more richer questions. So, but it's not just at Meta. I do want to share a couple of success stories like from our ecosystem where people have used Llama successfully outside of Meta. So this is an example of a group of people that use Llama for classification. They try to figure out, based on symptoms and description that the patients give to the nurses, how risky is the situation. And they use it successfully in Africa to be able to scale and be able to better triage patients. It's used for consumer engagement from, so Peridot, it's like, I don't know if you've played Pokemon Go, but it's like a similar game by the same company. And they use it to get like unique interactions based on the context in which the users are in. It was used for content generation for the Grammys and also to help with shopping experience for Audi. And then finally, on the B2B side, we've got companies like Kevlar, actually AI. That was part of our AI startup program last year with Meta in Paris and Station F here that uses it for cybersecurity, as an example. So if you want to get any updates on Llama and the latest things that are coming out, you can scan this QR code. And if not, thank you. And we have, I think, a couple of minutes if you have any questions.
All guests. Christian, thank you so much. For 30 minutes, the full room was super concentrated on your presentation. I think it's amazing. Thank you so much. And one more round of applause for Christian.
Thank you.
Next year, I wait the glasses, you know, we're going to do the presentation in them, right? So we're going to meet each other in at 15:45. And believe me, you don't want to miss this talk. I actually propose you to, keep your seat because the room is already full. And we're going to meet one of the speakers that already were there in this morning from Envisio. Stay tuned. Thank you. I don't know how you, but I just can't get enough everybody talking how NVIDIA technologies are amazing. So that's why we actually invited one of the best speakers that we could find in the world, to be honest, to talk about chips will never be enough. That person is VP Applied Deep Learning Research from NVIDIA. It's Bryan Catanzaro. Please welcome him.
Hello, everyone. I'm glad to be here today. What a great event. And thanks, Scaleway, for inviting me to come speak. When I was thinking about what might be most useful to the audience here at this conference, I thought maybe I'd talk a little bit about what NVIDIA does and what accelerated computing means to us. I think generally, it's not very well understood, the kind of work that NVIDIA does. People think of us as a company that makes chips. And we do. We make really awesome chips. But that's a very small percentage of the work that we do. And so I kind of wanted to reintroduce NVIDIA and the way we think about what we're doing so that maybe it can help us work together better as a community. Let's see. Oh, it looks like my slides. Oh, here we go. OK, slides exist. That's a good thing. Accelerated computing is really about co-design. It's about optimizing and rethinking everything from the algorithms, the applications, compilers, libraries, frameworks, networking, data center designs, cloud computing environments, and of course, the fundamental compute that goes into artificial intelligence. Ultimately, at the end of the day, when you are working in accelerated computing, what you're trying to provide, the product that you're trying to provide is time. You're trying to provide people the ability to do things computationally that they just couldn't do before in order to solve problems faster. And what this means is that by necessity, all of these different components, all these different technologies have to be built together and optimized together. Because if any one of them doesn't speed something up, if any one of them slows the whole thing down, ultimately you haven't delivered acceleration and you haven't delivered value. Now, another thing that's really important about accelerated computing is that it also implies deceleration. So it's not enough just to say, hey, I want my computer to go fast, because every computer is supposed to go fast. That's always been the goal of every computing system throughout all time, is to make compute go fast. But acceleration is really about specialization. It's about making priorities and making choices. It's about deciding what are the most important workloads computationally and then figuring out how to co-optimize every part of the system for that. And so that's the work that we do. I wanted to give you an example that maybe some of you aren't as familiar with from our graphics work. Something that I've been involved with. And then I'll talk about AI and how this works. Graphics is very compute intensive. It's where NVIDIA started. It's where we first developed our philosophy of accelerated computing. And these days, graphics is very computationally intensive. When we're doing ray tracing to simulate virtual environments, we're doing extraordinary amounts of computation per pixel, and we're trying to do lots of pixels and lots of frames per second. When we do native graphics, for example, in this particular game, we're getting about 23 frames per second, about 161 milliseconds worth of latency. We had this idea at NVIDIA to make graphics faster by doing AI, and we call that DLSS, stands for Deep Learning Supersampling. And what we're doing is rethinking the algorithms behind graphics fundamentally to take advantage of the redundancy that's in the work. If you think about it, there's a lot of redundant pixels in video, and that's necessary. That's where the structure comes from. Why should we actually compute every single pixel brute force? Why don't we infer it using AI? And so we built this technology called DLSS, and it's kind of crazy to think about accelerating something that requires so much compute and so much real-time constraints by adding artificial intelligence to it. But we did. And first we did super resolution, so that goes from 23 frames per second to 62. And then we built frame prediction. That's our most recent technology. It's getting up to 100 frames per second. As you can see, we're adding more and more AI, and we're actually making things go faster. So again, chips could never be enough, right? So if you just think about like how much work we're doing, we're increasing the amount of artificial intelligence that we're doing in real time with DLSS. But at the same time, the overall system is going faster, and the image quality is looking better because we found a smarter way of doing it. That's the kind of work that NVIDIA loves to do, is reconceive an entire application, the algorithms, and everything, all the software and the hardware, and co-optimize it for the most important workloads. I'm going to skip this in the interest of time. So generative AI is about computation, fundamentally. Past technologies were mostly retrieval-oriented. If you think about search or finding access to different media, it's been primarily about finding something, whereas generative AI is really a computation problem. Every time you ask a question, you're doing a lot of work. And training these models is also really intensive. The amount of work that goes into training has been growing at a crazy rate. You can see the blue line is before the advent of transformers. The green line is after transformers came about. And so we've been seeing a lot of change in the way that these systems are built. In 2021, we had a system inside NVIDIA that had 4,500 Ampere GPUs. 2023, 2 years later, we've got 11,000 Hopper GPUs. So the amount of compute for AI has gone up from 3 exaflops to 43. This is what acceleration can do. Of course, now we're working towards Blackwell. This is the foundation of our systems for generative AI. We've put in a lot of hardware and software to accelerate AI. And because of that, we're making the process of creating and deploying AI much more efficient. And that, of course, is going to lead to wider adoption of AI and better AI. There's this idea that when you make something cheaper, you actually end up using more of it. That's often called Jevons paradox. And it's something that we're always thinking about. How can we make this more efficient? Accelerated computing is the most efficient kind of computing. When you think about the amount of energy that's required to train or deploy a model, we're absolutely constrained by energy, and so we have to optimize the entire system to remove that. And in fact, if you compare the amount of machinery and energy that it takes to train a state-of-the-art model, with Hopper, 8,000 GPUs, 90 days, 15 megawatts. With Blackwell, 2,000 GPUs, 4 megawatts, a quarter of the power, but the same speed. So that's, again, accelerated computing. The amount of co-optimization that goes into all of that is pretty extraordinary. Mostly software. It's mostly software work. Now, as part of the full stack optimization that we do, we actually train our own AI models. We call them Nemotron. It evolved out of the Megatron project, Megatron being the biggest, baddest transformer. We have this open source project where we show our best techniques for training and deploying language models at scale on GitHub. And we figured once we have the software where we can train these models, we might as well train them ourselves. And in the process, learn the things we need to learn about how to create systems for artificial intelligence. And this, again, is very fundamental to this work of accelerated computing. You know, if we weren't training our own artificial intelligence, we wouldn't know how to build systems for artificial intelligence. That's what accelerated computing means. And you know, our goal with these models is to enable AI for every business and grow the ecosystem for AI. You know, NVIDIA is a company that loves to support other companies, that loves to partner with other companies, and loves to help them. And you know, because we're training our own models, we're hopeful that they'll be helpful to some folks. And you know, we have to do that in order to do our main business of accelerated computing. And so we might as well you know, add capabilities to our platform because of that work. We also have this idea of NVIDIA inference microservices, which I think is pretty important. You know, I've been mostly talking about training, but inference is becoming more and more of our business. So when we're thinking about accelerating computing, we need to think about how are these models going to be used, how are they going to be deployed, and how can we accelerate that? And you know, there's a lot of challenges. There's a lot of diversity of hardware, a lot of diversity of models and software, and so the idea behind NIMS is that we can package up a model, and it's going to be optimized for all of the different platform technologies that NVIDIA has, running on every GPU, running on the cloud, running on premise, and you know, we hope that that makes it a lot easier to deploy the very best models in the most efficient way. So just to conclude, you know, the work that NVIDIA does, you know, we sell GPUs, and so people often think of us as a chip company, and of course we're really proud of the chips that we make. But chips could never be enough. If we just built chips, all we could talk about is how fast the chip is in kind of an abstract sense, like how many operations per second it could do in some sort of abstract way. What really matters at the end of the day is not the chip itself, but what can you do with it. And that means that we have to go through this full stack optimization process. And that also means that we have the opportunity to rethink everything. In a time where the fundamental computational engines are changing, you know, the AI is growing, the amount of investment that's going into compute for AI is just staggering, and it's amazing to see. But that really changes the kind of things that people are doing. It changes the systems that we're building. At the same time, you know, the semiconductor technology is evolved. It's reached a point of diminishing returns. You know, we're not getting the Moore's law scaling that we used to, which means that you can't just continue to turn the crank and get a better chip every year. You have to really rethink, what are we doing with this? How are we going to optimize the whole system? Rethink everything. And you know, DLSS is a fun example of that, where you know, we thought, hey, this problem could actually benefit. We could make it computationally cheaper by using AI in a new way. We changed the algorithm and made it 5 times more efficient. It's time to be doing more of that for artificial intelligence. You know, we desperately need training and inference to be more efficient, and so that's the kind of work that we love to do at NVIDIA, is rethink everything from first principles, and then, you know, let's see what we can build. It's a lot more than chips, and I've mentioned all these things. They're all jointly optimized, you know, we're training our own foundation models in order to do that. You know, it takes actually a lot of understanding, a lot of experience training these models in order to know how to build systems for that. So we're doing that, and as part of that work, we're providing models, both open weight models as well as in other ways. And we're trying to make it easier for everyone to deploy these models with NIMs. And then the last point that I wanted to leave you with is that now that we're in this era of generative AI, it means that compute is the central problem in all the work that everybody is doing. And that's a new thing. It didn't used to be like that. But I expect that we're going to see an increased emphasis on all of this full stack optimization because that's how we're going to make AI progress. Thank you.
Bryan, thank you so much. It was amazing. I think rethink everything is going to be the mojo of this event, right? We're going to see each other in 5 minutes. We're going to talk about open source GPU clusters with Dell Technologies. Stay tuned. Don't be late. Okay, we're gonna start in a few seconds. Please take your seats. I see on the backs. That's great. So we're gonna talk about managing GPU clusters with open source. We're gonna talk it with an expert from Dell, AI CTO. Please welcome Maciej Mazur.
Hello and welcome everyone. So I hope that you are in the right room on the manufacturing track. We will be talking about factories. Okay, cool. So what I wanted to talk about today is something that we call Dell AI Factory. We are in a very nice and privileged position that we are able to work with a lot of amazing companies all around the globe, building their environments to train their large language models, to give them to people in forms of APIs or applications. And after delivering multiple of such projects, we figured out some patterns, figured out a couple of things that work, and most importantly, the ones that don't work, coded them into infrastructure and published into the open source community. Because we heard a lot today about open source models. That's a very important part, but also the software that is running the underlying operations, making the GPUs available, running your Kubernetes cluster, it's also part of the open source community, and we wanted to highlight that a little bit and show you guys how we use it. So the Dell AI Factory is a concept that came out from a business need. We started first delivering server storage and networking, as you might know Dell is doing for many years, and we saw that this is not working great in the beginning because people experienced low utilization of their infrastructure. We started investigating the issue, and we figured out that the main reason is the combination of hardware and software together and how this is actually being run. There were a lot of places where GPUs were allocated just fully as part of the VM, obviously not very efficient, like not using mix slicing, not using any more advanced technology to share the infrastructure. Also, the observability part, like how this is monitored, and all the other operational aspects were completely wrong. So we thought, OK, how can we help? And we decided to basically make available a Dell AI Factory, which is something that is a combination of hardware, software, and the services. So basically, we build it up, test it out, benchmark it in a factory, and we are able to deliver it towards the end users directly into their location where they can start using it. And what is super important is that this is not only something that comes with our hardware, that's also something that is published and available for you guys to reference and take a benefit from. So first of all, we publish a thing called Dell Validated Designs. And this is the description of how the solution architecture looks like, and also the infrastructure as code part on how to deploy it. What is super important, this also comes with our results of our validation. So whenever a new model is coming from Meta or from Mistral, we are taking it into our labs, run the proper testing cycle, and figure out that, OK, so on this hardware, with that operating system, that Kubernetes distribution, VLLM, and that combination of software, we can achieve this time to first token, that amount of tokens per second, and so on. So that this is also something that is available. The easiest way to get it is to just go into the Dell repository on Hugging Face, where you can directly see all of those documents. And this is something that helps you if you don't want to think really that much about the solution architecture. The second thing that it's coming with is the setup that helps you to run the day-to operations. So all the automation that is used not only to deploy the environment, but also to manage it efficiently whenever you are through the entire life cycle of it over a couple of years, or even more depending on the type of the environment. CV patching or upgrading or making sure that you are able to extend the environment with additional nodes. That's something that is coming with that setup. And we obviously don't do it by ourselves. We leverage the tremendous effort being done by the entire open source ecosystem and also a lot of partners that are delivering those pieces. But the good part is that this is all coming under basically our support. So whenever something is not working, there is one phone call to be made. What is also super important is that we are focusing on increasing the GPU utilization. We started from seeing initial customers having basically manually allocated GPUs on a whiteboard. It's like, hey, my team uses this today, towards like a modern, proper MLOps platform with things like schedulers like Volcano, a lot of automation, and basically being able to allocate based on priority, based on the end user, and also based on the metrics coming from the system. What was also very important for us is being able to make it heterogeneous so that you can pick your own hardware. In a lot of places, the availability of specific types of hardware is not that easy, and people have to mix and match in order to be able to go forward with their business. So we started testing out different things. Over recent couple of weeks, we managed to run like PyTorch training jobs with MPI operator on NVIDIA and AMD GPUs pulled together into one training cycle. So there are things that you can do to actually use your infrastructure more efficiently by all of those ways. What was also very important for us is that there are different people having different needs using that stuff. So we basically started looking into every UI and every API that we expose from a couple of different perspectives. So the simpler example would be the observability stack. If you look at the observability needs and talk to SREs or DevOps team, they will want to see like how much lifetime do I have on my disk? What is the CPU usage on that cluster? Do I have enough storage space to run something? But there will be a data engineering team that will be looking at completely different metrics. They will be hosting models on production. They will be looking at the tokens coming per second. They will be looking in classical ML and things like precision, recall, accuracy, completely different things, but still logging into the same environment. And the business team, in a, I don't know, banking fraud detection use case, they will be looking about frauds being made, or on another example, like a chatbot assistant, how many questions are being asked. And this is all available in Grafana Prometheus combination. But depending on who is logging in, you will get completely different graphs and different metrics exposed to you from the environment because you might be interested in a different thing. And that expands to also how you consume that infrastructure. So for us, it was very important to give people what they need. And obviously, most of the end users will want either like an endpoint, an LLM API, or they would want a UI where they log in. But there will be teams who are running RAG pipelines, doing fine-tuning operations, and they will prefer to log in to their favorite MLOps platform, open a Jupyter notebook, don't really worry about the complexity behind Kubernetes, about bare metal, about the GPUs. The smaller group of people, but also very important, will be the ones that are more advanced. They will expect to get a ready-made Kubernetes cluster with all the GPUs, fast storage, InfiniBand, Ethernet hooked up, but they don't really want to manage it by themselves. So they want to just bring their own MLOps tools because they know better how to build their pipelines. Last but not least, you will have teams that know how to get every last like 0.5% of their environment, and they will want a bare metal resource pool allocated to them. And you can achieve all of this from tools like Metal as a Service, from Kubernetes clusters, and so on. So you can build an open source stack that allows you to run that environment. So we also wanted to go with that approach, looking into building blocks, looking into a software-defined setup, and taking a lot of efforts that we did on the HPC space. So we have a tool called Omnia. It's open source, available on GitHub, that tries to make it easy to deploy types of environments that I shared earlier. It started with a HPC deployment for Slurm clusters, boring stuff, old legacy stuff, for something that they are still doing. But the modern environments, even on the HPC side, look like this. So you have your Slurm mix with Kubernetes. You have default Kubernetes clusters with Kubeflow. And Omnia as a system allows you to deploy and manage all of those different clusters, taking into account the users in mind. And just in the interest of time, what I wanted to also mention is that this gives you a full stack. So you can deploy not only the infrastructure part, but also the pieces that are necessary from your GPU providers. You can deploy the model registries and the repositories from where you can get additional packages, and the whole automation for day one and day two operations. I'm a bit out of time, but if there are some quick questions, happy to answer them. Thank you.
I'm sure people are going to have questions. You can still always come, and meet our speakers after the session. And we're going to meet each other very soon, so stay tuned. I think it's going to be like in 5 minutes, maybe a little bit less. Thank you so much. So, how are you feeling? All good? Prepared for an amazing next topic? Because we're going to talk about mid-frontier AI for software development. And we're going to have here one and only Vítor Monteiro, Head of Solution Engineering from Poolside. Please welcome.
Hi, everyone. Pleasure to be here. Thank you for the invite. So humbled to be here next to other fantastic speakers and members of the audience. My name is Vítor Monteiro. I'm a computer scientist by trade, but I spent the last 10 years working closely with customers, most of that time at GitHub, and then a little stint at Postman, and now I'm at Poolside. So our co-founders were here last year, and I'll talk a bit about them in a second. But if you don't know, Poolside is pursuing AGI in the domain of software development, and I'll explain how we plan on getting there. From the very beginning, we decided to take no compromises, and we ended up building pretty much everything in-house. Of course, part of this dedication to software development implies building foundational models specifically for that effect, but even what we call the model factory and everything that goes into the aspect of training frontier models, we pretty much decided to take no compromises, and to be able to control the experience end-to-end, we had to take this approach. To understand how we got here and a lot of the decisions I'm going to talk about next, we should really, for you that don't know the founders that were here last year, to understand how they came to build this company together. So Jason, who I worked for at GitHub, was responsible for things like GitHub Actions and incubated things like Copilot. And he met Iso during that period, and Iso almost sold his company to GitHub at the time, and they became very good friends. One thing to know about Iso is that he's been pursuing AI for software development and how AI can help in software development before it was popular, before it was easy, before attention is all you need. So this has really been his life mission and a passion that Jason adopted recently with the two of them. So our goal ultimately is that we believe that we will achieve AGI for software development, and when that's the case, you will have AI as a product and a whole development team. We're not the only ones that believe that. I think Sam Altman speaks that when he refers to the 1 billion person company. So who's developing the software in that company, I ask? Well, in my mind, it's Poolside. And there are stages to this. This is a very long goal, and it will take years for us or anyone else to get there. And those stages are, for example, the AI as a junior developer. Currently, we're kind of stuck in this code assistant land. And we've been here for a few years, where they're getting better, the models are getting better, but it's still very much me asking a model, an extension to help me with something. I want to quickly get to the point where I could see this experience as having someone from the audience next to me that's thinking alongside me and helping me go further faster as a colleague, instead of being kind of literally an assistant that I have to poke every time I need help with. So we believe we have a solution to bridge this gap. So how do we go about it? So we think that there are two key bottlenecks, and I think one of them is obvious. The first one is compute. So we're very privileged that recently we got investment from our investors to build the GPU farm necessary to build the large models we need to build. And this is the first bottleneck that companies get presented with. If you were at Poolside when this was announced, this for us was not a matter of celebration and hooray. We take this as a massive responsibility. There's so much good research in the industry. There's so many papers out there that could use compute to prove at scale. So we see this as a privilege, and we take this as a responsibility to now apply some of the things I'm going to show you at hyperscale and to bridge that gap. The other bottleneck is a bit harder because you can't necessarily buy that with money, even if you have lots of money. That bottleneck is data. So there are around, 3 trillion tokens of source code, which you would probably not use all of it anyway, around the world for training. So we all, even if we have the compute, are all training with the same data. So how do we address this particular bottleneck? So this is the area that we focused a lot of our efforts in the first year of the company, which is a way to generate as much synthetic code data as compute allows us to do so. And now with the compute that we have, it allows us to generate a lot of it. This can get very technical very quickly, and I get super excited with this, so I might kind of go down a big rabbit hole very, very quickly. But imagine this. And imagine, this is real, so you have to imagine, I've seen it, that we have a completely automated system that goes out there to the open source repositories on the internet and qualifies and selects repositories. I'll tell you how many in the end. But imagine that there's just this bot scanning and finds a repository. Then it qualifies if this repository can come into our farm. So is it high quality code? And does it have a way, and this way can expand and grow over time? But basically today is it covered by unit tests? So if anyone did a change to this project, would I be able to validate that the change was in fact a valid change or an invalid change? So that bot brings the repository to the farm, and then what it happens is it goes through the revisions of that repository, and even that is a selection process, and takes a revision, hides it from our model, from the models we're building to do AI code assistant in this case, for example, and asks the model to come up with a solution. Not just one solution, but 40 or 50 solutions with some variants, and we produce 50 different solutions for that problem. So imagine one project, one revision, 50 solutions. That code didn't exist before. So that is what we call synthetic code data. The best thing about that data is if you think how models and LLMs in generally learn, it's just a probabilistic way to predict the next token. And when you're consuming that data from places like GitHub, you're just consuming the end goal. You're just kind of reading and ingesting that data and predicting the next token. The brilliant thing about this system, which we call, by the way, I haven't said, reinforcement learning from code execution feedback. It's a nice five-letter acronym to remember. With this system, we have an oracle of truth. So when we ran that change, that one of those 50 changes that our model ran, we know if that change should take as positive feedback or negative feedback, because even if the model suggested something that failed all the tests, that's good data, that's valid data. And it's high quality because we can deterministically say that that's good and that's bad, not because we ingested a lot of it, but because we actually tested it. So now imagine, as I am speaking here to you, this is running live for hundreds of thousands of repositories. So on a daily basis, we're generating tokens and tokens and tokens of data that accumulate to the one that already exists, and it's all high quality data. So with this, with the principles that to bridge this gap, first of all, you need to train models which are specific for software development. And we don't believe that large language models are the futures for domain-specific problems like driving, medicine, software, etc. And then the ability to give it much more data than the data that exists today. So, and the last point, something I didn't mention on this talk because it doesn't pertain to the models itself, is that the reason why a lot of you haven't used poolside, or maybe some have because we do give access to members of the public to give us feedback, is that we focused first not on a SaaS offering, but on an enterprise offering. There's already a lot of solutions on the SaaS space, and we plan on getting there at some point. But today, what we see is that a huge demand of us building these frontier models, putting them behind a company's firewall and allowing that company to fine-tune on their data sources without being too concerned where that data goes, where that data travels, etc. So these are some of our pillars for the upcoming quarters. Today, and I'll show you the demo, something the co-founders couldn't show last year, but now I can. if you see that line and if you see that bridge, we have to compete on the code assistant arena until our models get smart enough to make that bridge and become my colleague, my co-senior developer, etc. So today, the customers that use us do it through the IDE, so JetBrains, all the JetBrains IDEs, Visual Studio Code, Visual Studio, Web Assistant, and we're API first. So anything we build, and the stuff you'll see, you could have built yourselves using our API, and I find that pretty special. But overall, we think we're going to stop talking about these extensions as the code assistant as we go through that curve, because as the models get much and more capable, what you will see is companies and individuals building a lot of apps, think about agentic, that are self-sufficient throughout your whole software development lifecycle. So we're talking about things that people already see today and play with today, from code reviews to just tidying up everything around the software development lifecycle. So I've recorded this because I wouldn't trust the Wi-Fi to do this live, but this is my own playground. And this is a small snippet, and I'm a bit late on time, a small snippet of my playground. Yeah? Video? Okay. So this is, for example, this is just a mobile app that I use to play with prompting, with poolside, and what you see here is the chat extension, and you'll see code complete on the left. Here, what I did is I just kind of showed how to retrieve live content from the internet. So I asked what's inside the following URL, and then basically asked poolside to replace the content of this screen with the content of the URL. Bit of the detail, I was super ambiguous in the prompt because I tried to challenge the model to actually think and understand the code a bit better. So now it's basically generating a diff that I can review and apply either block by block if I click review, or apply directly. I scroll up in a second to actually show how ambiguous that prompt was, because I really didn't give any structure on anything like that, as you can see here. So code completion is going to pop up pretty quickly at the bottom. So our code completion model is something we ship alongside the chat model. You can see here it just added 2 screens. I'm in front of this. So you can see it added the screens, it added the tokens, and now I like to show that you wouldn't necessarily delete that to be code complete, so you just ask chat to convert that code, and this is just my way of showing you the review process and the implement button. So like I said, today, customers that use us find our code assistant code completion extremely helpful already, but we want to do much more. In this case, an experiment I do is just asking for a complete rendering of a screen. So I just say, create a scrollable list with job openings, make it pretty, don't overlap with a notch, and I usually expect poolside to just give me the complete solution, and I iterate over that. So in this case, he gave me the whole file, I replaced it, and it gave me the functionality as I asked, and now I asked for some more job descriptions, and I asked to change the styles a bit, like, can you make it bold instead? So I can test the scrolling. This is something you would have seen in other code assistants. All of this has pretty much been built by a team of 20 people for the most part of the beginning of this year. And now that we have our GPU cluster in place for the next 2 or 3 years, we're pretty sure that we're going to prove the theory and the research that we did at this small scale and explode it. And maybe we can be here next year to show you where we are in that trajectory and hopefully have bridged that gap to show you an even more impressive demo. Thank you very much.
Vítor, thank you so much. I can't wait next year to see you and all the results. So we're going to meet each other at 1640 with a panel talk, and we're going to talk about how to build trustworthy AI. Difficult topic, amazing speakers. Stay tuned. So we're going to meet amazing 3 speakers who are going to talk about building trustworthy AI. So let me invite them to the stage. It's going to be Alex Combesi, Lionel Guillu, and of course, Sophie Monnier. Welcome.
Hello, can you hear me also in the back, everyone? Good. So, hi everyone, and thanks for joining this panel on building trustworthy AI and ensuring accuracy and explainability across sectors. You may have noticed Antoine Borde from Helsing is not here. He had a last-minute meeting he had to attend, but that's all right. We're going to do this roundtable with our 2 distinguished experts here. And before we dive into the discussion, I'm going to let them introduce themselves first, quickly. Maybe Lionel, we can start with you.
Sure. Thank you, Sophie. Nice to meet everyone. I can't see you, but hopefully you can see me. So my name is Lionel Guillu. I'm VP of Technology Development at Okine. And so I work in the branch that develops diagnostic models in oncology using AI. So a brief introduction, I'm an engineer and scientist by training, did most of my career in California, and then came back to France 2 years ago to join Okine.
And Alex?
Hi everyone, so I'm Alex Combesi, co-founder and CEO of Giscard. It's a company we created in 2021 to address quality and security challenges of AI systems when used in a critical context. So what we do to help understand and mitigate those risks is we provide testing methods for AI systems, and most specifically on generative AI systems.
All right, so today the topic is explainability. Why are we talking about explainability? It's been a topic that's been on the table for several years now, right? So let's say the canonical example comes from the banking sector, where an AI algorithm should be able to explain every single prediction it makes, for example, in the context of a credit loan. Now, there are several things we can explore, several questions we can ask ourselves. One question is how explainability is going to be used in practice. Is it going to be part of human decision-making, or is it going to be part of an automated decision process? Are we going to use it only in a proof-of-concept phase or in a deployed product? There are questions about explainability levels. Do we care about global explainability and to understand what features are important into making predictions in general? Or are we interested in understanding why a model made a particular prediction, so local explainability, and what are the methods associated with these levels? And in the end, there's also the question of the usefulness of it all in the end, right? So how useful or mandatory is explainability from a user experience or regulatory point of view? Or are there other factors at play that might have higher stakes than explainability in itself? So we're going to explore all of these points today. And maybe we can start with a first question for you, Lionel. Could you explain in which context you use explainability at Okine, and also what methods you use in healthcare?
Absolutely, so I can explain explainability, let's see. So just for a bit of additional context on the modalities of data that we primarily work with in diagnostics. So we do oncology once again, and the way we do this is taking histology slices. So think of it essentially as a slice of ham, except that it's from the human body. It typically contains a part of tumor. And so then, most of the models that I'm going to be talking about today are related to computer vision. So that's just for the general context. So for us, explainability, in the context of making medical devices that use computer vision, has 2 main use cases. The first one is when we build the model, we want to make sure the model is doing things that make sense. Okay, so we make the model tell us, for example, which part of the histology slides it focused on to make a prediction. And we always review this with pathologists and oncologists to make sure that the things the model are doing make sense. And we are to some extent correlated with known scientific knowledge that you can find in the literature. So that's use case number one. Use case number two is very different. So you were talking about development versus production. Use case number two is then production. For us, what production means is a pathologist typically using our model and trying to come up with a diagnostic on a particular patient to make a treatment decision. And so in that context, although there's no regulatory requirement for it, we always provide some layer of explainability so that the pathologist may have a critical eye on our prediction and decide whether he or she agrees with our prediction. So in terms of method, I'm not going to go into the method just now because I've talked for a while. Maybe Alex wants to chime in before I get into the technical details.
Yeah, so explainability is a very interesting topic. It's actually the topic that we started the company on 3 years ago because my co-founder had a PhD specifically on explainable AI. And what we found out is that explainability of AI models, when you ask to real users, whether they are the AI engineers or the end users, is something that everybody says that they need to have. So this is why we used this as a starting point. But what we realized when we started by deploying some automated explainability features, people actually, they use it once, but they don't necessarily come back to it again. So actually, this does not mean that explainability is useless, but explainability has a use in a specific context. One, because at the beginning, before you deploy a system, you need to develop trust. Developing trust is not just about technical features. It's also about trying to understand, getting used to the system. And explainability is very important when you're in this deployment phase to build trust, especially for people that are not technical. It's also definitely very useful when you're in the development stage, because when you're debugging, when you're improving the model, having some explainability features actually helps you understand where your model might have some biases, etc. But the thing is, once you've done that, these, like the adoption or the debugging, these are useful in a limited time. Because after you deploy, actually, on a running AI system, once it's running, people just want the prediction. They don't want to come back and debug, try to make sense of the explanations. So that need kind of disappears, and this is why maybe it's a segue for the next part of the discussion. We kind of pivoted away from explainability to work more on testing, because testing is something that can be automated, because explainability cannot be automated. The whole concept of explainability is that it's an interface for machines to explain themselves to humans. But if you remove the human of the equation, you cannot have explainability. Explainability only makes sense in the context of us as people. And if you want to automate in production, actually that's where something like tests are more reliable and you can automate. Because in the end, that's what we want to do, right? We want to deploy AI systems at scale. You'll have to iterate and renew them regularly. And you want to automate. Every week, when you have a new hospital or a new agent, you want to be able to have systems that are self-nourishing and self-updating.
Maybe just a follow-up question on something that you said, that you would use explainability at the beginning, especially to build trust. Depending on the models that we use and their complexity, sometimes you have these questions or opinions that explainability is somehow opposed to model complexity. What do you think about that?
Very complex question, because it's fairly straightforward to explain a local prediction. It's computationally expensive, but you can, and actually it's a requirement in some fields. You need to ensure that if someone has a question because they dislike a particular prediction, you are able to give this person a human understandable explanation of this particular prediction. But once you have done that, it only tells you about one case. So it's very hard to make sense out of it. And then what people really want to do is to understand the model globally. But the challenge here is that there's a real trade-off in terms of performance. The larger the model, the harder it is to really understand it at global level. Like how, so we're working on large language model systems. How can you really understand it? Of course, there are some like raccourcis, shortcuts, like at the start of the NLP journey, I think even before attention is all you need, you had word2vec. I don't know if some people remember word2vec. Yeah, a little. And there was this very neat explanation of like some kind of arithmetics you could do where you take king and you remove man, and that yields a vector close to queen. So yeah, of course, that kind of explanation is neat, but it's a fallacy to think that just because of this explanation, we could really be able to understand a model that has millions and now billions of parameters. So it's a little tough. I think Yann LeCun was, as in many things, I think was right, because back in I think 2020, he said something I think was very true at the time it was Twitter, saying that people, I'll paraphrase, people trust planes not because they are able to understand or we can explain why planes fly. Like maybe some of you know the physics of how planes fly, if you remember university days, but that's not the case. People trust planes because they've been tested through rigorous stress tests by regulators. And he was making this point to say that like explainability is, he was exaggerating, as always, with Yann LeCun, but saying it's useless. People don't need that to trust the system.
Maybe Lionel, you would have a comment because you use different kinds of models at Hawking, deep learning, or also more simple models.
Yeah, it's. I mean, some of the comments are similar. Some we diverge. As I mentioned, we do care, in production to have some layer of explainability. But for me, I really don't oppose it to model complexity. So we have some cases where the model are kind of by design explainable. So you get the explainability kind of for free in that case. And even in cases, at least in computer vision, where they're not by design explainable, it's not that hard to add kind of post hoc some layer of explainability on top. And so that means you're really not limited in the kind of models you can do. Just because you need to add explainability afterwards. However, I think where the experience in medical device that I have is very similar to what Alex is saying, is explainability is not the main fight. The main fight is demonstrating generalizability, that the model works in different contexts. And this is what we spend 95% of the effort on, and this is what we get challenged on by the regulator. And I think that makes sense.
Okay, so we're gonna go on this point of generalization or robustness in general. Just one question before that to tackle some sort of elephant in the room. Healthcare is a very certification-heavy sector. So I was wondering, what bigger part explainability plays in the certification process, and the AI Act is going to be implemented in 2027. What is it going to change for you concretely going forward at Hawking?
So in your first question on the role it plays today, my broad answer would be quite small. So you have 4 kinds of validation you need to do in medical device. Without getting into all the detail, one of them is called usability testing. It's essentially making sure that your target end user is able, with the instruction you provide, to use the device as intended. I think that's the only concrete example where explainability plays a role. And typically, that's not the validation where you fail. Now, your second question was, what was going to be the impact of the AI Act? So I think, like many companies, we hired outside counsel to try to see, kind of do a gap analysis between what we do today and where we need to be. And here, the takeaway, I was surprised, is actually that the delta is quite small. I might even be tempted to say non-existent, in the sense that all the logic they have in terms of traceability, in terms of documentation, are things that you have to do in the medical device sector anyways. And actually, I think we're discussing, maybe it's the same in other sectors as well, that have some kind of history, some kind of legacy of being regulated already.
So on your side, Alex, you work with, customers from very different sectors. How constraining do you see the AI Act being for Giscard moving forward?
At Giscard, we do businesses with large regulated industries, from banking like BNP, or insurance like AXA, in the industrial sector, Michelin. They are usually not necessarily regulated, but they have this very strong culture of risk management or quality management. Usually, the keyword quality management is something linked to manufacturing. Risk management is at the very heart of the business model of banks and insurance companies. And sometimes, for banks, there are regulations around risk management. And that has profoundly modeled these companies in a way that they already do a lot of what the AI Act is doing. I salute the kind of courage and ambition of the regulators when they started working on the AI Act about 4 years ago, trying to establish a general purpose, somewhat cross-domain regulation of AI. It's a little tough because when you look at different industries and types of companies, the practices of that are, you have really stark gaps. You have banks, healthcare providers, etc., who are almost ready from day one because it's things that they already do, versus startups, versus AI providers, versus GenAI, where GenAI, it's like a brand new field and it's much harder. So sometimes it's not that people don't want to comply with the EU Act, it's just that sometimes it's very hard to know what to do, because some AI systems are kind of very old and understood, and some are very new, like generative AI is very new. So there's this ongoing work. What people need to understand is the EU AI Act is only phase 1. Then there is, well, the phase 2. Each European country has to apply to translate it into their own law, right? And that has not been done yet today. And then something that has already started is the translation of these texts into standards and codes of conduct that give more precise guides on what to do. And on this one, I mean, it takes time, but I'm a little disappointed that the AI Act was passed without these codes of conduct, etc., ready. So this yields a temporary situation, which is a little tough, especially for startups, where there's a bit of a gap where people don't have a codes of conduct yet. Fortunately, I mean, to give a signal of hope, like, let's all remember that this UI Act is going to be in place in 2027. They actually, in the final decisions, decided to give 1 more year. It was supposed to go in 26, which was definitely not really realistic. but still today, I mean, we're waiting. The timelines for a lot of the final codes of conduct and the norms is early 2025. I do have sincere hopes that by the AI Action Summit, which is in February next year, I'm genuinely hoping that these different codes of conduct and standards will be ready by then, because it will really clarify the path for especially AI startups, which are, as I understand, a little bit lost.
And now if I take up on a comment that you made, Lionel, that explainability is actually a small part of your validation process, right? So it's not in itself the major hurdle in deploying at scale an AI system, but more what you call the validation or generalization or robustness. Let's dive a little bit into that. Like, could you tell us what robustness or generalization means for you at Okin, and how do you test for it?
How do we spend 95% of our time? Yeah. Okay, so it's quite a complex question. So I'll try to keep it fairly high level without being vague. So essentially, there are some things we do that I think are not specific to us, that are going to sound very familiar to anyone doing AI. And then some things that are going to feel maybe a bit foreign and that have more to do with medical devices. So I'd say first thing we do is quite standard in AI. So it's all the kinds of techniques you can do to ensure you have a robust model. So you do data augmentation, you take diverse training data. I think like pretty much everyone now use foundation models. Before using downstream models, I think it's become quite universal. So, we use regularization, all the kinds of machine learning tricks you could use to make sure the model you have is robust. And I think all of that is quite standard. I think the way in which, I think what happens after, which is the way we test it and the way we control it, maybe is a bit more unique. So I'll pick maybe 3 examples of what we do after. One of it is clinical validation. And typically when you hear about a medical device, this is what you hear about. So it's how does my model perform in an external setting? And so you want to do that in diverse cohorts, in diverse populations. Maybe we'll talk about that after. What does it mean that it's diverse and why do we need it to be diverse? So that's step 1. Step 2, I think, is an idea that, in my opinion, is quite underused in AI in general. That's called analytical validation. And so think of it as you kind of pressure test the model. You modify the inputs in all sorts of ways, and you want to get a consistent output. So the reason you do that in medical device is very simple. When you have a patient, you want to ensure that whatever happens in between the patient and the result is always the same. But a lot of things happen in between, which essentially are all the preparation step of your sample. So in our case, you take a physical piece out of the body, you cut it, some human cuts it, preserves it in alcohol. There's all kinds of steps that have to do with staining, selection, putting on a slide, scanning after, so you can use all kinds of different scanners. So all the steps you have between the patient and the model could trigger some differences. And so that's actually one area that's quite unique, but I think could be generalized notionally to try to think of cases where you want the model to have the same output with diverse inputs and try to come up with quantifiable metrics to ensure this is the case. And then the third bucket of things we do have to do with when you deploy your medical device at a given pathology lab or a given hospital, you want to be able to guarantee its performance in that setting. And so one of the techniques that we use for that is calibration. And essentially little tweaks. I really wouldn't call it fine-tuning, but it's little adjustments you can make on site to guarantee performance at that hospital.
And in your case, Alex, so you want to deploy like automatic testing, as you said, it's not like for human validation behind. So how would you make sure your models, your LLMs are robust, and what kind of tests do you deploy for that?
Thanks, Antoine. Actually, I think some of the techniques that we use are the same for computer vision and for regular machine learning models. So things like metamorphic testing, where you change the input and you see how the model behaves. That's, I think, one of the staples of robustness testing. We also have methodologies where we evaluate the performance across different slices of the data to be sure you don't have because the trick with robustness, it's all about going beyond the aggregated performance. Because at a certain point, after, as an AI engineer, you've done enough work, you get to 70, 80%. Like the global metric starts to hide the flows, right? And you want to identify on which slices you have these issues. But when you work with LLMs, these techniques don't work anymore. So we had actually a year ago to when we extended to LLMs to completely rethink and redo a lot of research into how to ensure the robustness of LLMs. And there are different techniques, but the number one is really being able to generate realistic evaluation data set. That's because the issue, automate. So I want to make it clear for LLM, we don't pretend we can automate 100%. We can automate it after there are some human inputs to validate generated data sets. But the goal is to be able, not with a complete rollout of a chatbot, to be able to simulate realistic attacks, realistic difficult questions that the users may ask. And then, that's the other side, that's also pretty hard, use LLMs to evaluate the logic or the factuality or the toxicity, different metrics of the outputs of the LLM system. So I want to make it clear for LLM, if you want to understand the robustness of LLM, you have to generate data and you have to embrace like LLM as a judge. Because, I mean, the alternative is literally, and some people have tried that, it's literally people manually writing questions and manually reviewing every single answer. And that's, I mean, people, some have tried, but that doesn't scale. So LLM, actually, what we found is when they are used in the right context to generate adversarial data sets and to evaluate models, so we have fine-tuned models, fine-tuned system just for evaluation and generation purposes, can be very helpful, not in automating everything, but getting started with realistic data sets and realistic rules for toxicity, etc., that then humans can review and validate much quicker than if they were to do it by hand.
I think there would also be a lot of things you could say about generating diverse data sets in the context of medical devices. We're kind of reaching the end of the panel, but if you could just give info in a few words.
Yeah, and I think one thing that's very specific to medical devices is you also have the ethical component, right? So you essentially want to try to ensure that your medical device is efficacious on as broad a population as possible. And also avoid the kind of bias, for example, age, gender, race, and ethnicity are the big ones you're trying to watch out for, and to make sure that you've controlled and you've checked for these biases and that you're robust to them.
All right, then this concludes our panel for today. So thanks everyone for joining and listening to us.
Thank you, Sophie.
Thank you.
Thank you.
Thank you. Thank you so much. One more round of applause for our speakers for being here. Such a great, respectful discussion. Thank you so much. Yeah, you could leave it here. All good. So we're going to finish this. So, are you ready for the last session in 5 minutes? Is there anyone in the room, by the way, you can raise your hands, who have been here since the beginning? No one? No one. Okay, well, we hope to see you at the end in 5 minutes. You definitely heard about the launch of this product because it was super viral. You definitely heard her voice, so stay tuned. Don't be late. We're going to come in 5 minutes. I see people coming. We're going to give you a few seconds while I'm introducing the last speaker of the day, but definitely one of the best. We are so happy to see him here because this product is so viral. I hope you tried it, by the way, and you've been to it today in the morning session too. So please let me welcome, and it's going to be really warm welcome on your side. Please, it's the last session here on Master Stage at Station F. So, no further ado. Next session is Moshi's Behind the Scenes, from conception to inference. And we're going to hear from the CTO, Laurent Mazaret-Putai. Whoop, whoop.
Hello, everyone. Thank you for attending this talk. It has been a great day so far. You had so many interesting talks. I hope you enjoyed it so far. And hopefully, it will be worth it for this last talk. So I'm going to present you Moshi behind the scene. It will be a bit of the story of how we created Moshi, starting roughly 6 months ago. We'll see a bit about Moshi, the model itself, about how we trained it, but also about how we run inference and how we actually did the open source release that happened a couple of weeks back. So yeah, that's the plan for the talk, and let's dive straight into Moshi. We released the model back at the beginning of July, and Moshi is actually more than your usual text model. It's really a full speech-to-speech model. It's a bit similar to human beings in the sense that it would listen, think, and speak at the same time, same as you would do. You can try it online already. It's on moshi.chat. You can have 5-minute talk sessions with it. And you also have an open source release, so that if you want to run it locally on your computer, it's also possible. So yeah, a question that we get quite often is, why did we build Moshi? There are already so many voice AI, things like Siri or Google Assistant that get used tens of times per day. So we did Moshi because we felt that the interaction with these models were a bit artificial. It's not like if you were talking to a real human being. And it's largely due to how these models are built. So these models tend to use a very cascaded setup. It means that you have a long pipeline before you get the output back. First, the model has to detect with what we call a VAD that you finish talking. And only at this point, the model will transcribe what you said to an actual text, feed it to a large language model, get back the textual answer from the model, and then some audio will be synthesized again. So you will be back to a voice, and it will be played to you. So you will have a latency that will range from like 3 to 5 seconds, which is much less lively than with a human being. However, if you do you also lose emotions and speaking style of the user because you go through a text version of what they're saying, which is not the case with Moshi. So another limitation of voice AI is that they tend to also be half duplex. It's a bit similar than when you're talking through a walkie-talkie, in the sense that only one person is speaking at the time, either you or the voice assistant. And you have to press the button to change between people. Whereas when you're using a phone with a friend, both people speak at the same time and people interrupt themselves, and it makes for a real conversation. So it's what is called a full duplex setup, which is something that voice AI tend not to have out of the box. Typically, in an English conversation, you would have something like 5 to 10% of overlap between speakers, and that's something that Siri would not model for you. So yeah, a typical way to, doesn't match my slide. So the question is, how can we make the current setup better? So this is what Siri will do. And instead of going through this whole pipeline, we would rather go directly from audio to audio. The model will do everything for you. And the simple idea for that will be to just feed the audio directly in the model. So right now, we're able to train LLM pretty efficiently. However, if you try to put an audio signal in a large language model, it's slightly problematic because of some complexity constraints. That is, if you consider the sentence Qtai is an AI lab based in Paris. This sentence, it actually has 8 words and not 7. It's super easy to fit in a large language model. Even if it's like a 7 billion parameter transformer, this kind of model, it will run through 50 tokens, 100 tokens per second without any issue on commodity hardware. However, if you try to put audio instead of a text there, then the signal is much larger than that. So for audio, typically, you would get value 24,000 times per second. That's not even for high quality, that's just for speech quality. And you do that for, let's say, it takes you 3 seconds to say this. Qtai is an AI lab based in Paris. So you end up with 72,000 values to fit through the large language model. And that's not something that you can cope up with in something like 3 seconds. Your model will not be real time. So you have to do better than just feeding the audio directly through the model. And the idea there was to actually compress the audio before feeding it through the large language model. So we already have ways to compress audio. You can think of MP3, which is what is called a codec. It's pretty efficient, but what we use is much more efficient than that. It's called MIMI. It's a neural codec because it's based on neural networks. And rather than dividing the size of the audio by factors of tens, it will divide it by thousands. So we were saying before that we go from we have 72,000 values for the whole audio. Here we will have 12.5 steps per second. And for each step, you would have 8 values that are returned, that each value is more and more refined and have more details about the audio to be played. But that's something in total of 100 values per second. So in total, for the 3 seconds, you have something like 300 values, and it starts to be something that a LLM can cope up with. So yeah, we could try just passing these 300 tokens directly into the transformer, and that would work. I said before that the transformer can do something like 100 tokens per second. So you play this 300 tokens, and you're roughly real time. But still, it's slightly problematic because your hardware has to cope up with the 100 tokens per second in a continuous mode. It cannot afford to drop a frame or anything like that, or you will hear some audio glitch. So it will be pretty challenging for commodity hardware and probably a no-go if you want to play it on a mobile phone or some weaker platforms. So instead, we use a slightly more complicated model, which is called a hierarchical transformer. So rather than going through the whole transformer for the 300 value, we group them. We only go through this big transformer on each time step. So we go through it 12.5 times per second. And each time, it will return what we call some continuous embeddings, like a set of values, thousands of them. And then we will run a much smaller transformer on these values. And this smaller transformer, we will have to run it something like 8 times if we want 8 levels of details, or 16 times for 16 levels of details. But as it's only 600 million parameters in our case, it's something fairly small, and it's no problem to go real time on that kind of thing. And these values, they will be injected back into the big transformer so that it actually sees the values that has been produced. And this way, we can just iterate things. It's your usual autoregressive model. So yeah, we can just take that and use it as an autoregressive model. So it's really just predicting the next most likely chunk of audio. And it acts a bit like a normal LLM. You feed it with a prompt, and it's able to do the most likely continuation. So we have a sample there where we have...
Listen to your sister, Morty. To live is to risk it all. Otherwise, you're just an inert chunk of randomly assembled molecules drifting.
So you've heard this kind of 5 seconds of audio. And just after that, we run the model so that it will predict what is the most likely future for this. And the model doesn't really have an agenda or anything like direction where it wants to go. It's just what it feels is the most likely.
And listen to your sister, Morty. To live is to risk it all. Otherwise, you're just an inert chunk of randomly assembled molecules drifting in the gases in a vacuum of space-time. Live and love.
So you can hear that the model has preserved the voice of the characters because obviously it's the most likely thing that it could do. So yeah, once you have this autoregressive model, you want to build a dialogue model on top of it. Right now, it's just a continuation model. It's a bit like the GPT of ChatGPT. But you want the chat version. You really want to be able to have a conversation. You don't want the model to use your voice to say random things. So to do that, you have to separate two different roles. The role of Moshi, which is the voice AI assistant, and the voice of the user, which will be the gray token there. One way to do it will be to just interleave the two things, and that's what you can see here. But it doesn't really work well if you do it that way, because you're kind of in the same setup as like the half duplex thing. You're in walkie-talkie mode where there is only either yourself speaking or Moshi speaking, but there is no both of them speaking at the same time. And to get around this, what we did is do what we call multi-stream modeling. So it means that Moshi, the model, is actually modeling both the audio stream for the assistant and also for the user. So it will take as input the two audio streams and generate both of them. So in a way, Moshi is actually trying to predict what you're going to say. So it will know slightly in advance what you're trying to do and act based on that. During inference, obviously, we don't really care about this prediction. So we don't do the inference, like the last bit of the inference that generates these values. We don't run it because we don't need it. But during training, it's something that Moshi learns about. And yeah, so with that, you feed both the Moshi tokens in brown there and the gray tokens that come from the user. And this one, they just come directly from the microphone. Moshi will predict its next brown values. We will just re-inject them to the model and take the next slice of audio from the microphone, and then we iterate. So yeah, now we have some insight about how the model works, and let's see how it was trained. The training setup is actually fairly complicated, so it's just a basic summary of how it's working. It has a certain number of stages. Like the first one is we train a text model that is called Helium. It's a 7 billion parameters model, and it's trained on something like 2 trillion tokens. Once we have this model, we start training an audio model that is initialized with the weights from Helium. So this model will already have some models that came from the text. And this model, it will be trained on unlabeled audio data with the corresponding text. So at this stage, you don't have the two streams. There is just one stream of audio, and the model tries to predict, again, the next most likely chunk of audio. So it understands how audio works. It understands what is a voice and what is keeping the voice of someone. It even understands what is music and is able to keep the pulse of a music and all that. And once you've done this training, so this training is fairly long, like it's running on millions of hours of audio. And once you've done that, you want to add the multi-stream data. So that's the third step. At this point, we don't have good quality data, so we just use what is called diarization to separate the speakers in an audio file. So we split by speakers a chunk of an audio file, and we just say, again, walkie-talkie mode. We have one person speaking, the other. So you won't have really interruptions that are well-modeled and that kind of thing, but you will have the notion of two speakers that Moshi will learn during this third step. And after that, the fourth step, which is the critical one, it's fine-tuning on real two speakers audio with separate stream. And there, it's very important that you have lively interactions, that you have interruptions, and that you have all the things that you were not able to carry in the previous steps. So yeah, the last step is very challenging, and it requires very high-quality data with separated channels per speaker. And this kind of data is pretty rare. So there are existing data sets, but they tend to be small and with poor quality. So Fisher has 2,000 hours of phone calls, but phone calls are just super bad quality. And also, it's pretty old. It doesn't have much diversity. So for that, we didn't have much choice but generating synthetic data. So generating synthetic data, we use actually our own text model to generate the script for the data. We could try to use existing interaction data that get used to train textual model, but the problem with this is that they're really tied to textual model. So they will produce code, or they will produce long list of bullet points, the things that ChatGPT will do. But these things tend not to work very well when you're having a conversation with someone. You don't want it to say 10 bullet points in a row. So instead, we fine-tune Helium to generate really conversation data. And based on this conversation data, we wanted to generate some audio. So we developed our own multi-stream text-to-speech system that would convert it to audio. In a way, it's a setup that is very similar to Notebook LM. We just generate, in the end, lively interactions between two speakers, and that's really what Moshi needs to be able to be Moshi, a useful voice AI assistant. So we still need to bootstrap a bit the data. We cannot do full synthetic. We need to have some ground truth about interaction. And for that, we use some voice artists, in particular Alice, that was the voice for Moshi. And so they did for us multiple scenarios, things with emotions and so on. And we fine-tune our text-to-speech system on this data so that we can generate an arbitrary number of speech. So now we listen to a small extract where it's actually not Alice that is speaking, but instead our text-to-speech system that is speaking, and where it's ranging over possible intonations and tone of voice.
Hey, this time I'm not chatting, but rather being controlled by text. I can express more than 70 emotions and speaking styles. Like whispering. Or maybe I could sing a song. I can sound terrified. Or impersonate a pirate, ahoy matey.
I can even speak with a very French accent, just like my inventors.
Looking forward to interacting with you.
OK, so that's our text-to-speech system. Once we've generated the text dialogue via Helium and apply the text-to-speech system there, we add, like, again, something that looks a bit like Notebook LM. In the interest of time, I will just skip that.
Hello.
And we'll go directly to the next slide. So that's it for the training part. And now that we're able to train good audio models, we also want to be able to test them in a real situation. So the challenging bit there is that there is no clear metric about what is a good interaction with audio. You don't have things that you have for text model like quizzes or things that they're good at answering at, because qualifying how interesting conversation is, it's actually pretty challenging. So to be able to say if the model is good, we needed live interaction, and we work on real-time inference for that, so that we can just play with the model directly. Here you will see a footage of Alex actually using a very old version of what we called the Moshi station. So it's just a Moshi model that you can interact with like live.
You speak like a pirate. Oh, you mean in a thick southern accent? Yeah, exactly. Like, I'm a southerner, and I know how to talk with a drawl. I mean, I know how to say y'all and thank y'all, and I can whip up a good old barbecue.
OK, so that's a very old version of your UI. That's from April or May, like that's only like 4 months after we started or something like that. And you can see that Alex actually had to hit the space bar, because at this point, you still had to do the end of terms manually. Nowadays, it's all automated, and Moshi will model that for you. And also, like the terminal, the UI is pretty like it's just a terminal thing. So it's not ideal if you just want to use it directly. So there are specific constraints just to develop this Moshi station and this real-time voice AI. And it's mostly about being able to produce audio token like in real time, so you cannot afford to like miss a deadline. You need to produce some audio chunks every 80 milliseconds, and if you just miss one, then there will be an audio skip, and the user will be able to hear it. And don't get me wrong, there are some audio skips right now. It's far from perfect, but we work hard to reduce most of them. So we wanted to optimize a lot the overall latency of our system for that. And by latency, we really mean the time spent from the input in the microphone to the output in the speakers. The model has a theoretical latency of 2 audio frames, so that's 160 milliseconds. And the latency that in the end we will want to achieve, it's that we achieved is 200 milliseconds. So it's 160 milliseconds plus 35 milliseconds of compute time. And there is 5 milliseconds that is spent somewhere in the network because you're talking to a web UI and all that. So with that, Moshi is able to answer and react to what you're saying in 200 milliseconds, which is quite comparable to what human beings are doing. And even as Moshi is kind of predicting what you're saying, Moshi also knows when you're going to finish a sentence. And obviously, for the sake of the demo, we tweaked it so that it's very aggressive in its way of thinking and will start pretty quickly to talk, which is something that you cannot do with other systems. And yeah, so we provided a web UI so that users can actually interact with it without having to go through the Moshi station and the terminal UI, which is not that great. The processing is done in the cloud. So the nice thing with this web UI is that you can run it on a mobile phone. You don't need to have your own GPU to actually run that stuff. Initially, we had servers in Europe and in the US, but to minimize latency mostly, because from the US, if you have to query a server in Europe, then you need to add tens of milliseconds to go through the Atlantic and then back. But nowadays, we only have servers back in Europe, but because we're open source, you can just run the model locally, and you will have a perfect latency. So yeah, that's a schema of the whole infrastructure that we use. I'm just going to skip that because it's a bit too complex anyway. One thing to mention is that the backend of Moshi, it's entirely written in Rust. So it's not using your go-to programming language, which is Python, for most of the modeling. And the idea there, it's much easier to deploy a very stable infrastructure using this programming language. So the code base had been very reliable. We actually didn't have to make any modifications since the first day where we released the model back at the beginning of July. The only thing that we did is actually refreshing the model once to give it new capacity. And we also use a framework that is called Candle to write our model. And the nice advantage of this framework is that it has native support for quantization. So actually, when you run the online version of Moshi, it's quantized so that it's more efficient, but it's quantized in such a way that it doesn't lose too much quality. There is a bit of a disadvantage though, in using Rust there, is that you have 2 different code bases, one for inference, one for training, so you have to be pretty careful about lining them up. So a few words on how we optimize things. One saying is that if you cannot measure it, you cannot improve it, which is when you want to actually optimize some code, the first thing is to actually know where the time is being spent rather than just having an intuition of that. And we spent quite some amount of effort being able to extract profiles on our code and also being able to monitor real-time performance of our code. Here you have actually a sample trace of our code, so that's an inference step. You can see Mimi encoding the audio, then the big transformer, then all the small transformer step, and the decoding. And we spent numerous hours looking at this kind of plot and trying to squeeze things out, trying to find where time is used not to actually do some computations. So that's one thing. And the other tool that we had is observability. So that's the dashboard of Moshi. It represents the current number of users in production. And the nice thing is that it also tells you the latency measurements that we have with Moshi. So you can see whenever someone is skipping some audio, you will see there a failure. And that's something that has also been super helpful in developing our inference platform. And yeah, finally, some stats. We serve 500,000 sessions, median session time like above a minute. Initially, we had 200 GPUs. There are only a couple of them nowadays that we have the open source release. And again, almost no maintenance needed. So there I had a demo of Nell playing with Moshi, but we won't have time for this one.
Hello,
either.
what's up?
And let's just skip to the open source announcement. So we wanted the community to build on Moshi. And for that, we needed two things. We need to release the source and the weights. And we did that under a permissive license so that everyone can reuse both of them. And we also wanted to do what we call open research. We want to document the methodologies that we used to build Moshi so that others can do the same things and can also improve the things that we didn't do properly. And for that, we published very long technical reports that you can find on arXiv. So that's an extract of our technical report. It represents the benchmarks of MIMI or neural codec on like some standard benchmark. And again, it's key not just to drop a model out and say, oh, it's the best model in the world and that's it. We really want to put numbers behind it and to say that kind of thing, it's doing it really well. But that other kind of thing, it's not the best and it should be improved. So there we have an example of a thing that it's actually not doing well, and it's what we call the modality gap. It's actually, you ask Moshi lots of questions and answers. It turns out that the text model is doing well on these questions and answers. It answers correctly 56.4% of the time, whereas when prompted with audio, Moshi only answers correctly 23% of the time. So we still have a big gap there, and it's something that we're working on, but us and the whole community. And that's the point of releasing the methodologies so that people can just, from there, get this score a lot higher. And yeah, we wanted also Moshi to be able to run locally. So we did a release, so not only of our production code base, which is in Rust, but also a code base that is in PyTorch, so that it's easy for people to hack around it, and a code base that uses a framework called MLX from Apple that makes it possible to run Moshi on your MacBook, so that everyone can use Moshi at home. The real advantage of the thing is that the audio never leaves your computer, so it's very good for privacy. You don't need to send it to a server and have someone that tells you, oh, it's safe. In that case, you know that it just stays there. You can actually try it yourself. You just have to run these two commands and just go on our GitHub, and you will find these commands and a lot of other details. And yeah, that's a demo of Moshi talking to Moshi. But again, in the interest of time, I won't have time for it. You can find it on Twitter at Oni, who actually made the demo. If you go on our GitHub, there is probably a link to that too.
Oh, hi.
Let's just skip that. Well, that's it for the origin story of Moshi. Again, you can find it online, and you can just try it out on moshi.chat, but there are only a couple GPUs, so there might be a waiting queue if there are too many people trying to use it at the same time. But in that case, I really encourage you to download Moshi, install it on your computer, try it out, and play with it. If you have any feedback on that, obviously we have a GitHub, so feel free to enter issues and tell us how you feel about it. Well, thank you for your attention.
Thank you, Laurent. Thank you.
Yes.
I guess next year, Moshi going to present Rick and Morty, the continuation. Dear audience, this is our last talk. I would like to take a few seconds just to thank... Oh, no? No, okay, that's it. I would like to thank you, each of our speakers, for their dedication, for their insight that they shared with us and with you today. And you online in the room, thank you so much for your time. Thank you for staking. Thank you for being so energetic. It was really an honor to be your MC. Thank you so much, and see you hopefully next year. Bye.
you.